Somewhere above you, right now, a clock is running out. It belongs to a star with a name, a measured distance, and a death already written into its physics. When that clock reaches zero, the star will collapse in less than a single second, and then it will release more energy in a few weeks than our sun will produce in its entire lifetime. The light of that death will cross the dark for centuries before it reaches your eyes. And here is the part that should make the hair on your arms rise. By the time you see it, the killing will already be over. The radiation will arrive at the same instant as the light. There is no warning. There is no early sign in the sky. The flash you see and the dose you absorb are the same event. This is not a story about the death of stars. Stars die constantly. In our galaxy alone, a star detonates as a supernova roughly once or twice every 100 years. Somewhere in the wider universe, a star is exploding every single second of every single day. No, this is a story about something far more specific and far more personal. This is a story about the distance between you and that explosion. Because death from a stellar explosion is not a question of whether. It is a question of how far away, and how often, and which direction the blast is pointed. It is a statistics problem. And when you actually run the numbers, the statistics are far stranger, far closer, and far more frightening than almost anyone realizes. Let me show you the shape of the threat. A supernova is the most violent ordinary event in the cosmos. When a massive star runs out of fuel, its core collapses to a density so extreme that a single teaspoon of it would weigh as much as a mountain range. The outer layers crash inward, rebound, and blow the star apart at nearly 10% of the speed of light. For a few weeks, that one dying star can outshine the combined light of every other star in its galaxy. 100 billion suns outshone by one corpse. Let that sink in. And that is just the ordinary kind of death. There is a rarer, sharper, more terrifying kind. When certain massive stars die, they do not simply explode outward in all directions. They focus their fury. They channel a beam of gamma radiation out of their poles, a beam so concentrated and so luminous that for a few seconds it becomes the single brightest object in the entire observable universe. We can see these beams from across 13 billion light-years of space. We have a name for them. We call them gamma-ray bursts. And here is the question that keeps a certain kind of scientist awake at night. What happens to a planet that finds itself standing in front of one? So here is what we are going to do tonight. We are going to put real numbers on the danger. How close does a star have to be before its death threatens everything alive on Earth? The answer has a precise value, and it has been calculated, and it has been revised, and every revision has made the danger zone larger, not smaller. We are going to ask how often Earth has already been hit. The answer is written in the rocks beneath the ocean floor, in a radioactive fingerprint that should not exist, and yet it does. We are going to name the stars that could do it. They are real. They have catalogue numbers. One of them was nicknamed the Death Star, and for years scientists genuinely worried it was aimed at us. And we are going to ask the most unsettling question of all. Have stellar explosions already killed most of the life that has ever existed on this planet? Because there is a growing case that one of the 5 greatest mass extinctions in Earth's history did not begin on Earth at all. It began in the sky with a beam of radiation fired from a dying star thousands of years before the first creature on Earth felt it. By the end of tonight, you're going to understand exactly how the universe kills with light. You will understand why a star you cannot even see could end you. You will understand why distance is the only thing standing between life and a sterilized planet, and why that distance is smaller than it sounds. And you will understand the strangest truth of all, the one we will build toward through everything that follows. The same explosions that can erase a biosphere are the explosions that built your body. Every atom of iron in your blood, every atom of calcium in your bones was forged in one of these deaths. The thing that can kill you is the same thing that made you. We are walking, breathing assemblies of stellar shrapnel, asking how likely it is that the next piece of shrapnel has our name on it. The villain of this story has no face and no malice. It does not aim for us. It does not know we exist. It is simply physics, indifferent and enormous, releasing energy on a scale the human mind was never built to feel. A supernova does not hate you. A gamma-ray burst is not cruel. They are just very, very large numbers, and you are a very, very small and fragile arrangement of chemistry, and the entire question of your survival comes down to where you happen to be standing when the numbers go off. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand how a star kills, you first have to understand something that sounds impossible. You have to understand that for almost the entire history of human thought, nobody believed stars could die at all. For thousands of years, the sky was the one thing that never changed. Mountains eroded, rivers shifted, empires rose and collapsed, but the stars came back every night in the same patterns, fixed and eternal, and so people across every ancient culture reached the same conclusion. The heavens were perfect. The heavens were unchanging. Whatever lived and died down here, the lights up there were permanent. This belief was so deep, so obvious, that it became one of the central assumptions of natural philosophy for almost 2,000 years. The sky did not change. Everyone knew it. And then, one night, the sky changed. In the year 1054, by our modern reckoning, astronomers in China were watching the heavens when a new star appeared where no star had been. They called it a guest star. It was not faint. It blazed into the morning sky and grew brighter than everything except the moon. For nearly a month it was visible in broad daylight, a point of light burning in the blue, impossible to ignore. The Chinese court astronomers recorded it carefully. Observers across the world, from the Middle East to very likely the American Southwest, marked it down. And then, over the following months, it faded. After about 2 years, it was gone from the naked eye entirely. What those observers did not know, what they could not have known, is that they had just watched a star die. They were looking at a supernova, the violent end of a massive star, located roughly 6,500 light-years away. The light that reached their eyes had left that star around the time the first cities were being built on Earth. And when astronomers in the modern era pointed their telescopes at that same patch of sky, they found something extraordinary still sitting there. A cloud of shredded, glowing gas, expanding outward at over 1,000 kilometers every second, blown apart by the explosion those ancient watchers had recorded. We call it the Crab Nebula now. It is the most famous corpse in the sky, and it is still expanding, nearly 1,000 years later, a wound in space that has not finished opening. That guest star was the first crack in the ancient certainty that the heavens never change. But the crack did not become a chasm until a young man in Denmark looked up on a November evening and refused to believe his own eyes. His name was Tycho Brahe. In the year 1572, he was walking home in the evening when he noticed a star in the constellation Cassiopeia that simply should not have been there. It was brilliant. It was as bright as the planet Venus. And it was a part of the sky he knew intimately, a part where no such star had ever shone. Brahe was so stunned that he stopped people on the road and asked them to confirm that they saw it too. He thought perhaps his eyes were deceiving him. They were not. The star was real, and it was new, and according to everything educated people believed about the cosmos, it was impossible. Brahe did something that, in his era, was almost revolutionary. He measured it. Night after night, with instruments he built himself, he tracked the new star's position with a precision no one had achieved before. And he was looking for one specific thing. If the object were close to Earth, somewhere in the realm below the moon where change was allowed to happen, it should shift its position against the background stars as the night progressed and as the seasons turned. That shift is called parallax. Brahe measured and found nothing. No parallax, no shift. The new star was not a local phenomenon in Earth's atmosphere or somewhere near the moon. It was out there, among the fixed stars, in the realm that was supposed to be eternal and perfect and incapable of change. And it had changed. A star had appeared where there was none. The numbers were striking, and the conclusion was heretical. The heavens were not perfect. The heavens were not unchanging. Things up there could be born, or at least could suddenly appear and then fade away. Brahe published his findings, and the title of his work gave us a word we still use. He called the object a nova, Latin for new. What he had actually seen, we now know, was not a new star at all but a dying one, a white dwarf detonating in a thermonuclear blast. But the name stuck, and the dam had broken. The ancient sky, the perfect and permanent sky, was dead. The real sky was a place of violence. For centuries after Brahe, though, the true scale of that violence stayed hidden. People could see that a new star sometimes flared up. They had no idea what powered it. They did not know how far away the stars truly were. And without distance, you cannot calculate energy. And without energy, you cannot understand the threat. A bright light could be a candle nearby or a bonfire far away. To know how dangerous a supernova was, you first had to know how staggeringly far away the stars actually sit. And that number, when it finally arrived, broke something in the human imagination. Try to feel the scale for a moment. The Sun is the nearest star, about 150 million kilometers away. Light from the Sun, traveling at the fastest speed anything can move, takes a little over 8 minutes to reach your face. The next nearest star, Proxima Centauri, is so far that its light takes more than 4 years to arrive. To put that in something you can picture, imagine shrinking the Sun down to the size of a single grain of sand. On that scale, the nearest other grain of sand, the nearest other star, would be about 6 kilometers away. 2 grains of sand, 6 kilometers apart, with nothing but emptiness between them. Now scatter a few 100 billion of those grains across a region so vast that light itself needs 100,000 years to cross it. And you have the Milky Way. That is the ocean these explosions happen in. That is the scale. And it matters enormously, because it means that almost every star is too far away to hurt us. Almost. The villain of this story is not the explosion itself. The villain is proximity. And to understand proximity, scientists needed a way to measure the unmeasurable distances to the stars. The breakthrough came not from a famous astronomer with a great telescope, but from a woman working as a human calculator at Harvard, paid a few cents an hour to examine photographic plates, who noticed something that nobody else had noticed. Her name was Henrietta Swan Leavitt. In the early years of the 20th century, she was studying a particular kind of star, a star that pulses, brightening and dimming on a regular rhythm like a slow heartbeat. These are called Cepheid variables. Leavitt examined thousands of them, and she found a pattern so clean and so reliable that it became one of the most important measuring tools in the history of science. The brighter the true output of one of these pulsing stars, the slower its rhythm. Time the pulse, and you know the star's real brightness. Compare that real brightness to how bright it looks from Earth, and the difference tells you exactly how far away it is. For the first time, humanity had a cosmic ruler. We could finally measure the distances to objects far beyond our own galaxy. Leavitt's law, discovered by a woman who was not even allowed to operate the telescopes, is the foundation that everything else stands on. Without it, you cannot know how far a supernova is. Without distance, you cannot know if it can kill you. And once we could measure distance, the supernovae stopped being curiosities and became something terrifying, because now the energy could be calculated, and the energy was a number that did not fit inside the human mind. Consider what astronomers found when they finally understood what they were looking at. A supernova at its peak releases around 10 to the 44 joules of energy. Spelling out what that means in ordinary words is almost useless, because the number is so far outside daily experience that it loses all meaning. So let me try a comparison instead. Our Sun, over the entire course of its life, from birth to death across roughly 10 billion years, will release a certain total amount of energy. A single supernova can release a comparable amount in a matter of weeks. One dying star, in a few weeks, matches the lifetime output of a star that burns for 10 billion years. The numbers are striking, and they should be. This is the most energetic ordinary event in the universe, short of the very birth of the cosmos itself. But raw energy, at a great distance, is harmless. The light of a supernova in another galaxy is beautiful, not dangerous. So the real question, the question this entire story circles around, is this. How close does that energy have to be released before it stops being a light show and starts being a weapon? Where is the line? Where does the sky go from a spectacle to a sentence? The first serious attempt to answer that question with hard physics came in the early 2000s when a team led by the astrophysicist Neil Gehrels sat down to calculate what scientists began calling, with grim honesty, the kill distance. The logic was elegant and chilling. A supernova does not have to physically reach Earth to destroy life. It does not have to vaporize the planet. All it has to do is damage one thin, fragile layer high in our atmosphere, the ozone layer. That delicate shield of 3-atom oxygen molecules absorbs the most dangerous ultraviolet radiation from the sun before it reaches the surface. Strip away enough of that ozone, and the sun itself becomes the murderer. The supernova does not even have to finish the job. It just has to take down the shield and let our own star do the rest. Gehrels and his team calculated how much ozone a supernova would destroy at various distances, mostly through the flood of high-energy radiation and the cascade of cosmic rays it would unleash. And they arrived at a number. A supernova within about 8 parsecs, which is roughly 26 light-years, would destroy more than half of Earth's ozone layer. That is the threshold. Inside that radius, the death of a star could mean the death of much of what lives on Earth. The math is striking precisely because it is so specific, not a vague danger, a radius, a line drawn in the dark, with us on one side of it. And then the line started moving. Because as scientists refined the models, adding effects that the first calculations had left out, accounting more carefully for cosmic rays, and the longer-term damage to the atmosphere, the kill distance did not shrink. It grew. Later work pushed the dangerous radius outward, first toward 10 parsecs, then in some analyses toward 20 parsecs. The astrophysicist Adrian Melott, who has spent much of his career studying exactly this question, put it bluntly when he revisited the numbers. The earlier estimate of around 25 light-years, he said, was probably too small. The real danger zone, accounting for everything, might extend out to 40 or 50 light-years. And damaging effects, the kind that would not sterilize the planet but would still wound the biosphere and spike radiation levels at the surface, could reach out even further to well over 100 light-years for the most energetic events. Sit with what that means. The danger zone around Earth, the sphere inside which a dying star could devastate life, is not a tiny bullseye. It is a region tens of light-years across in every direction. And every revision of the science has made it bigger. Something about our first instincts kept underestimating the threat. We kept assuming we were safer than the numbers actually allow. There is good news buried in the foundation, and we should be honest about it, because honesty makes the rest more frightening, not less. When astronomers survey the stars within that 50 light-year danger zone, looking for any star massive enough to die as a supernova, they find none. The closest stars are small, calm, long-lived suns and dwarfs that will never explode. Proxima Centauri, our nearest neighbour at just over 4 light-years, will simply fade away over trillions of years, never detonating. So in the immediate sense, Earth is safe from a true extinction-level supernova right now. There is no loaded gun pressed against our temple in the local neighbourhood, but that safety is a snapshot, not a guarantee. The solar system is not sitting still. It orbits the centre of the galaxy, dragging us through different neighbourhoods over millions of years, into and out of regions thick with massive young stars. Right now, we happen to be drifting toward the Orion Arm, a region with more of exactly the kind of stars that die violently. Over the long timescales that the rocks beneath our feet actually record, Earth has not always been in a quiet neighbourhood, and the evidence that we have already passed through the firing line more than once is not speculation. It is sitting in the sediment at the bottom of the ocean, a radioactive signature with a story to tell. We will come back to that buried evidence, because it changes everything. But first, you have to understand the thing those ancient observers were really looking at when they saw a guest star bloom and fade. You have to understand exactly how a star turns itself into a bomb. And that process, when you follow it down to the final second, is stranger and more violent than the explosion it produces. Because here is what nobody watching the sky in the year 1054 could have guessed. The most dangerous moment in the death of a star is not the part you can see. The blinding light, the guest star, the weeks of brilliance, all of that is the aftermath. The real event, the event that actually kills, happens in the dark in less than a heartbeat, deep inside the star where no light can escape. And what happens in that final fraction of a second breaks the rules of ordinary matter so completely that physicists needed entirely new laws to describe it. To understand the moment a star dies, you have to understand the war it has been fighting for its entire life. A star is a balance between two enormous forces locked in a standoff. Gravity, relentless and patient, is always trying to crush the star inward, to collapse all that mass into the smallest possible point. Pushing back against it is the heat and pressure of nuclear fusion in the core, where hydrogen is being fused into helium, releasing energy and pressure that holds the star up against its own weight. For millions or billions of years, these two forces stay perfectly matched. The outward push of fusion exactly cancels the inward pull of gravity. The star is stable, the star shines. But that stability is a lie, because the fuel is finite, and every second the star burns brings it closer to the moment the standoff ends. For a massive star, a star perhaps 10 or 20 times heavier than our Sun, the ending is catastrophic. As it exhausts the hydrogen in its core, it begins fusing heavier and heavier elements to keep the pressure up. Hydrogen becomes helium. Helium becomes carbon and oxygen. The star burns through each fuel faster than the last, each stage buying less and less time. The carbon burning phase might last a few hundred years. The neon phase, perhaps a year. The oxygen phase, a few months. And then it reaches silicon, and the silicon burning phase, the final stage, lasts about a single day, one day. After millions of years of life, the star has one day left, and it does not know it. The star is now built in layers, like an onion of fire, each shell burning a different element, with the heaviest in the center. And in that center, the silicon is fusing into iron. This is the trap. This is the moment everything goes wrong. Iron is the end of the line for fusion. Every element lighter than iron releases energy when it fuses, but iron does not. Fusing iron consumes energy rather than producing it. So the instant the core becomes iron, the fire goes out. The outward pressure that has held the star up for its entire existence simply vanishes, and gravity, which has been waiting patiently for millions of years, finally wins. What happens next happens faster than you can think it. The iron core, roughly the size of the Earth but containing more mass than the Sun, collapses. Not slowly. The collapse happens in less than 1 second. The core falls inward at speeds approaching 70,000 kilometers per second, nearly a quarter of the speed of light. The temperature soars into the billions of degrees, and the matter is crushed to a density so extreme that the very atoms break down. The electrons are forced into the protons, and they fuse into neutrons, and in that instant, the core transforms into the densest form of ordinary matter that physics allows, a neutron star, an object with more mass than the Sun, packed into a sphere the size of a city. A single sugar cube of that material would weigh as much as all of humanity combined. And here is where it gets stranger. When the collapsing core slams into this new incompressible neutron core, it cannot go any further. It rebounds. A shockwave erupts outward. But that shockwave, on its own, is not actually enough to blow the star apart. For decades, this was one of the great unsolved problems in astrophysics. The math said the shockwave should stall, should run out of force before it could tear the star open. Something else had to be pushing, and the answer turned out to be the most ghostly particle in all of physics. When the core collapses and the protons and electrons merge into neutrons, that process releases an almost unimaginable flood of particles called neutrinos. Neutrinos are nearly massless, and they barely interact with matter at all. A neutrino can pass through a wall of solid lead a light year thick and most likely come out the other side untouched. Right now, trillions of neutrinos from the Sun are passing through your body every second, and you feel nothing, because they almost never hit anything. They are the universe's ghosts. And yet, in the heart of a dying star, the conditions are so extreme, the matter is so densely packed, that even these ghostly particles get caught. A tiny fraction of them deposit their energy into the stalled shockwave, and that is enough. That is what finishes the job. The neutrinos reignite the explosion and blast the star apart. Think about the scale of that neutrino flood. In the final seconds of a massive star's collapse, the core releases around 99% of the explosion's total energy as neutrinos. 99%. The blinding light, the guest star, the brilliance that outshines a galaxy, all of that is the remaining 1%. The visible explosion is the leftover scrap. The real event, the overwhelming majority of the energy, escapes invisibly as a tidal wave of ghost particles that pass straight through the dying star and out into space at nearly the speed of light. And in 1987, humanity caught that wave. On the 23rd of February in 1987, in a galaxy called the Large Magellanic Cloud, a satellite galaxy of our own Milky Way, about 168,000 light-years away, a massive star died. We named the resulting supernova by the year of its discovery. We call it supernova 1987A. It was the closest supernova observed in nearly 400 years, the closest since the era of Tycho Brahe, and it became the most studied stellar explosion in history. But the most astonishing part of the story is not what astronomers saw in their telescopes. It is what happened a few hours before anyone saw anything at all. Deep underground, in detectors built to catch neutrinos, 3 separate facilities around the world recorded a sudden burst of particles. A detector in Japan, a detector in the United States, a detector in Russia, all registered a tiny, brief flurry of neutrino events within seconds of one another. In total, across all the detectors, only about 24 neutrinos were caught. 24 out of a flood so enormous that the numbers defy belief. When that explosion happened, the burst of neutrinos that passed through the Earth numbered in the tens of billions for every square centimetre of the planet. Tens of billions of these particles passed through every fingernail-sized patch of your would-be ancestors' bodies, through the whole Earth, through everything, and we caught 24. And those 24 particles, arriving hours before the light, confirmed one of the boldest predictions in all of astrophysics. They proved that the death of a massive star really is, first and foremost, a neutrino event. The light is just the echo. That detection mattered for our story in a way that goes beyond physics. It told us that the warning, if there ever is one, comes in a form we cannot feel and can barely detect. The neutrinos arrive first, but they arrive only hours ahead of the light, and they pass harmlessly through us. By the time the dangerous radiation arrives, it arrives with the light, all at once. There is no air raid siren for a nearby supernova. There is only the flash, and the flash is also the blow. Now, everything we have described so far is one kind of stellar death, the collapse of a massive star. But there is a second kind, an entirely different mechanism that produces an explosion of comparable fury, and it is in some ways more relevant to the danger near Earth, because the stars that die this way are far more common and can lurk much closer to home without anyone noticing. This second kind begins with a white dwarf. When a star like our Sun dies, it does not explode. It is not massive enough. Instead, it gently sheds its outer layers and leaves behind its core a dense, hot ember about the size of the Earth, but containing nearly half the mass of the Sun. This ember is a white dwarf, and on its own it will simply cool slowly over billions of years, fading into the dark. Most white dwarfs end their existence this way, quietly. But some white dwarfs are not alone. Some of them orbit a companion star, locked in a gravitational dance. And the white dwarf, being so dense, can begin to steal matter from its partner, pulling streams of gas onto its own surface, growing heavier with every passing year. There is a hard limit to how much mass a white dwarf can hold. It is called the Chandrasekhar limit, named for the young physicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s while still in his 20s on a long sea voyage from India to England. The limit is about 1.4 times the mass of the Sun. And when a white dwarf, stealing matter from its companion, finally crosses that line, the consequences are absolute. The star can no longer support its own weight, but instead of collapsing into a neutron star, the entire white dwarf detonates in a single runaway thermonuclear explosion. In a matter of seconds, the carbon and oxygen of the entire star fuse all at once, releasing so much energy that the white dwarf is completely obliterated, leaving nothing behind. No neutron star, no remnant core, just an expanding fireball where a star used to be. This is what we call a Type 1a supernova, and it has a peculiar and beautiful property. Because every white dwarf that explodes this way crosses the same mass threshold, they all detonate with almost exactly the same energy and the same peak brightness. They are standard, and that standardness made them into one of the most powerful tools in the history of cosmology. Because if you know how bright something truly is, and you can measure how bright it appears, you can calculate its distance. These exploding white dwarfs became cosmic mile markers, visible across billions of light years, and using them, astronomers in the late 1990s made a discovery that overturned everything we thought we knew about the fate of the universe. But that is a thread we will pull on much later, because it leads somewhere unexpected. For now, what matters is this. There are two ways for a star to explode. A massive star can collapse, and a white dwarf can detonate. Both release a comparable flood of energy. Both can strip the ozone from a planet's sky. And the white dwarf path is the one that allows danger to hide. Because while astronomers can see massive supergiant stars from far away and know they are doomed, a white dwarf, quietly stealing mass from a companion, is dim, easy to overlook, and could, in principle, be lurking surprisingly close to us. In fact, the nearest known candidate for a future Type 1a supernova is a system called IK Pegasi, and it sits only about 150 light-years away. That is outside the immediate kill zone for an extinction event, but it is close enough to be a sobering reminder. The stars that can kill are not all giants you can point to. Some of them are small, patient, and easy to miss, slowly drinking from a neighbor until the moment they cross the line. So now we have the foundation. We know the heavens are not eternal, that stars die, and that their deaths come in two violent forms. We know that distance is everything, that the kill zone for an extinction-level supernova is a sphere tens of light-years across, and that every revision of the science has widened it rather than narrowing it. We know the explosion is mostly invisible, a flood of ghost particles, and that the killing radiation arrives with the light, leaving no time to react. And we know the danger is not purely hypothetical, because the solar system drifts through the galaxy into and out of dangerous neighborhoods over millions of years. But knowing the mechanism is not the same as knowing the threat. A loaded weapon is only dangerous if it is pointed at you, and only deadly if it has been fired before. And this is exactly where the story turns from physics into something closer to forensics. Because scientists did not just calculate that Earth could be hit. They went looking for evidence that Earth has already been hit. They dug into the ocean floor. They examined the soil the astronauts brought back from the moon, and what they found there, buried in the sediment, was a fingerprint that should not exist on Earth at all. A radioactive ghost from an explosion that happened before there were humans to see it. The foundation is set, the danger is real, and the rocks beneath us are about to testify that the firing has already started. Before we follow the evidence into the seabed, there is one more piece of the foundation that the entire statistics of death rests upon, and it is the most important number of all. How often does this actually happen? Because a threat that occurs once in the lifetime of the universe is not really a threat. A threat that occurs every few decades is something else entirely, and the supernova rate, when you measure it, sits in an uncomfortable middle ground that should make you pause. In a galaxy like ours, with its few 100 billion stars, a supernova erupts somewhere on average once or twice every century. That sounds rare, and on a human scale it is. Most of these explosions happen on the far side of the galaxy, hidden behind thick clouds of dust, too distant and too obscured for us to even notice without specialized instruments. The last supernova clearly seen with the naked eye in our own galaxy was the one Johannes Kepler recorded in the year 1604. 4 centuries have passed since then without another visible galactic supernova, which is, statistically, slightly overdue. Somewhere out there, in the Milky Way, stars have certainly exploded in those 400 years. We simply could not see them through the dust. But raise your view to the scale of the whole universe, and the numbers become almost incomprehensible. There are an estimated 2 trillion galaxies in the observable universe, and each one is producing supernovae at a similar rate. When you multiply it all out, the conclusion is staggering. Somewhere in the observable universe, a star is exploding as a supernova roughly once every second. Every time your heart beats, a star is dying somewhere. Every breath you take spans dozens of stellar deaths scattered across the cosmos. The universe is not a quiet, static place. It is a vast and continuous detonation, an endless cascade of dying stars, and we happen to live in a brief, calm gap between the explosions near us. That calm is what makes the comparison so unsettling. Think of the supernova rate near Earth not as a constant danger, but as a slow game of chance that has been running for billions of years. Over the 4.5 billion years that Earth has existed, even rare nearby explosions become near certainties given enough time. A supernova close enough to seriously damage the biosphere, within roughly 30 light years, is expected only once every few 100 million years or so. But Earth has been around long enough to roll those dice many times over, and a supernova at a moderate distance, close enough to leave a mark, but not to sterilize the planet, somewhere in the range of a few hundred light years, should happen far more often than that. Those moderate events, the ones that wound rather than kill, may strike every few million years. On geological timescales, that is not rare, that is routine, and the radiation does not arrive in a single form. When astronomers talk about the danger of a nearby supernova, they are really talking about a layered assault that unfolds over different timescales. First comes the prompt flash, the initial blast of gamma rays and X-rays traveling at the speed of light. Arriving the instant the supernova becomes visible, this is what would immediately begin tearing apart the ozone layer. Then, over the following months and years, comes a second wave, the supernova's expanding shell of debris, and the powerful shockwave it drives into the surrounding space, accelerating particles to enormous energies. And finally, over a much longer period, comes the slow grinding rain of cosmic rays. Charged particles flung outward by the explosion that can take thousands of years to wash over a nearby planetary system, bombarding the atmosphere, altering the chemistry of the air, and driving radiation down to the surface. It is this last component, the cosmic ray bombardment, that turns a distant supernova into a sustained menace rather than a brief one. A flash of light is over in moments, but a planet caught in the cosmic ray wash of a nearby supernova could endure elevated radiation for centuries or longer, the kind of slow, relentless dose that increases cancer rates, damages living cells generation after generation, and chips away at the ozone shield long after the explosion itself has faded from the sky. The supernova lights up for a few weeks. The consequences can last for thousands of years. Picture what such an event would look like from the surface of Earth. If one of these explosions happened just close enough. For weeks, a single point in the sky would blaze brighter than the full moon. Bright enough to cast shadows at night, bright enough to read by in the dark, bright enough to be seen in broad daylight. It would be the most beautiful and the most terrible sight in human history. And nobody watching it would feel the radiation already pouring through them, already beginning to dismantle the molecular shield that keeps the sun's ultraviolet fire from reaching the ground. The light would be glorious, the dose would be silent, and only later, as the ozone thinned and the burning began, would the true nature of that beautiful new star reveal itself. This is the foundation. Stars die in violence. Their deaths come in two forms, both unimaginably energetic. Distance is the only protection, and the safe distance is larger than we keep assuming. The explosions are frequent on cosmic scales, common enough on geological scales to have touched Earth many times. And the radiation comes in waves, some instant and some that linger for millennia. Everything about the foundation points toward a single, uncomfortable conclusion. If stellar explosions are this powerful, this frequent, and this far-reaching, then in 4.5 billion years, Earth cannot possibly have escaped them all. So the question stops being whether a star has ever fired on Earth, and becomes how many times, and how close, and what it did to the life that was here when it happened. To answer that, we have to stop looking up at the sky and start looking down, into the ground, into the layers of sediment and stone that have been quietly recording the history of our planet for millions of years. Because buried in those layers is a witness, a radioactive atom that has no business existing on Earth, that can only be made in the heart of an exploding star, and that has been found, again and again, in the seabed beneath our oceans. The sky has already fired on us, and the bullet is still in the wound. In the late 1990s, a group of physicists in Germany were studying samples of rock dredged up from the bottom of the Pacific Ocean, and they were looking for something that, by all rights, should not have been there. The samples were pieces of ferromanganese crust, a slow-growing mineral layer that builds up on the deep seafloor over millions of years, accumulating at a rate of just a few millimeters per million years. This makes it one of the slowest forming materials on Earth, and that slowness is exactly what made it valuable. A ferromanganese crust is a time capsule. Each thin layer is a frozen record of the ocean chemistry from a specific window of the distant past. Read the layers in order, and you are reading the history of the planet, stretched out across millions of years. The team was searching these layers for a particular atom, a radioactive form of iron called iron-60, and the reason they were searching for it is the reason this entire story exists. Iron-60 is not a stable atom. It is radioactive, and it decays away over time, with a half-life of about 2.6 million years. That number is the key to everything. It means that if you started with a sample of iron-60, after 2.6 million years, half of it would be gone. After another 2.6 million years, half of the remainder would be gone, and so on. The consequence is absolute and unforgiving. Any iron-60 that existed when the Earth first formed 4.5 billion years ago decayed away completely an unimaginably long time ago. There has been more than enough time for every last original atom of it to vanish. So if you find iron-60 on Earth today, fresh enough to still be detectable, there is only one possible conclusion. It did not come from Earth. It was delivered here recently, in geological terms. And there is only one place in the universe that manufactures iron-60 in significant quantities: the interior of an exploding star. The German team found it. Buried in the layers of that deep ocean crust, in a specific band of sediment, they detected an unmistakable spike of iron-60. The amount was tiny, just a faint dusting of atoms, but the detection was real, and it was confirmed, and then it was confirmed again by other groups, using other samples from other parts of the world. The signal was global, and when they read the depth of the layer, when they calculated how long ago that band of sediment had been laid down, they arrived at a date. The iron-60 had rained down on Earth roughly 2 to 3 million years ago. A supernova had exploded near our solar system, recently enough that its radioactive ash was still detectable in the ground, and the planet had quite literally been dusted with the debris of a dying star. Let that sink in. There is a layer in the ocean floor, and in that layer is the physical residue of a stellar explosion. You could, in principle, hold a piece of an exploded star in your hand, scraped from the bottom of the sea, atoms that were forged in the final seconds of a star's death, and flung across the light years to settle on our world. We have not just calculated that supernovae can reach Earth, we have found the evidence that one did. And then it got worse, because they found more than one. As the techniques improved and more samples were analysed, the picture sharpened into something even more startling. The iron-60 did not from a single event. There appear to have been at least 2 separate pulses of it, 2 distinct waves of stellar debris, suggesting that Earth was dusted not once but multiple times. One major signal centered around 2 to 3 million years ago, and evidence of an earlier deposit further back, perhaps 6 to 8 million years ago. And the iron-60 was not only in the oceans. When scientists examined the lunar soil brought back by the Apollo astronauts, the same radioactive fingerprint was there, embedded in the surface of the moon. The moon has no ocean and no atmosphere, no way to wash the signal in from elsewhere. The only explanation is that the moon, like the Earth, was directly bathed in the fallout of a nearby supernova. 2 worlds, our planet and its companion, both carrying the same radioactive scar from the same cosmic event. So how close was it? This is where the investigation became genuinely tense, because the answer determines everything about how dangerous the event actually was. The amount of iron-60 that survived the journey, combined with models of how supernova debris spreads through space, allowed scientists to estimate the distance. The early estimates placed the explosion at a few hundred light-years away, perhaps around 330 light-years. At that distance, a supernova would have been spectacular but survivable. It would have blazed in the sky as bright as the moon, visible in daylight, a second beacon hanging in the heavens for weeks. It would have bathed the planet in elevated radiation, but it was probably too far to cause a true mass extinction. But then the distance estimate started to move, just as the kill distance had moved before it. Adrian Melott and his colleagues, revisiting the data, argued that newer analyses pointed to the supernova being significantly closer than the first estimates suggested. Their revised figure cut the distance roughly in half to something more like 150 light-years. And at 150 light-years, the event stops being a harmless light show. At that range, the cosmic ray bombardment would have been intense enough to penetrate deep into Earth's atmosphere, to increase the radiation dose at the surface, to potentially affect the climate, and to leave a real biological mark, not an extinction, but not nothing either, a wound. And here is the part of the investigation that turns the whole story personal. The timing of that supernova, around 2 to 3 million years ago, lines up with something significant in the history of life on Earth. It coincides with a period of climate upheaval, the transition into the Pleistocene, an era of expanding ice ages. It coincides with a documented elevation in extinction rates. Not a catastrophic mass extinction, but a measurable uptick in species dying out. And it coincides with a dramatic environmental shift in Africa, where forests gave way to open grasslands and savanna. Some researchers have proposed something genuinely provocative. They suggest that the increased radiation and cosmic ray flux from that nearby supernova may have altered cloud formation and atmospheric chemistry, nudging the climate, drying the forests, opening the landscape. And the opening of the African landscape, the shift from forest to grassland, is precisely the environmental change that many scientists link to a crucial turn in the story of our own ancestors, as forest-dwelling creatures were pushed onto open ground, where walking upright on two legs became an advantage. The implication is almost too strange to state plainly. A dying star, hundreds of light-years away, may have reached across the void and reshaped the environment of our distant ancestors. The same explosions that can kill may have, in this case, shoved the course of life on Earth in a new direction. We cannot prove it. The connection is suggestive, not certain, and many factors shaped that era. But the possibility alone tells you how deeply intertwined the fate of life on this planet is with the deaths of distant stars. We are not separate from the violence of the cosmos. We are inside it. We have always been inside it. Now follow this further, because the Iron 60 led scientists to an even larger realization about where we live. When they looked at the broader structure of space around our solar system, they found that we are sitting inside something strange. We are inside a vast, nearly empty cavity in the interstellar medium, a region where the gas is far thinner and hotter than the surrounding galaxy. Astronomers call it the local bubble. It is enormous, a cavern in space, roughly 1,000 light-years across, and our solar system is currently drifting through its interior. For a long time, the origin of this bubble was a puzzle. What could carve out such an immense, hollow region in the gas of the galaxy? The answer, it now appears, is a series of supernovae. Over the past 10 to 20 million years, a cluster of massive stars near our region of the galaxy died in a sequence of explosions, and the combined force of those blasts swept the gas outward, hollowing out the cavity we now live inside. The same population of dying stars that carved the local bubble is very likely the source of the Iron 60 in our oceans. We are not just near where supernovae have happened. We are living inside the blast cavity they created. Our solar system is currently passing through the scarred, hollowed-out wreckage of a stellar killing field, and we have been doing so for millions of years. The walls of the bubble around us are the shockwaves of stars that died before our species existed. And it gets worse, because this realization completely changes the statistics of the threat. If the Sun simply sat in a quiet, average patch of the galaxy, the odds of a nearby supernova would be one thing. But the Sun does not sit still, and it does not travel through average space. It bobs up and down through the galactic plane as it orbits the center of the Milky Way, and that motion carries it into and out of the spiral arms, the regions where massive stars are born and die in great numbers. We are currently drifting toward the Orion Arm, one of these dense, active star-forming regions. Over millions of years, the solar system's journey takes us repeatedly into neighborhoods where the supernova rate is far higher than average. The quiet we enjoy right now is not the normal state of affairs. It is a temporary lull between passages through more dangerous territory. This is the core of the problem. and it is far more serious than the simple question of whether any single star near us is about to explode. The real threat is not one star. The real threat is time and motion combined. Given enough millions of years, and given that our solar system keeps wandering into the firing range, the question of whether Earth will be struck by a damaging stellar explosion is not a question of if. It is a question of when and how badly. The iron 60 in the seabed is not a one-time fluke, it is a sample. It is proof that the firing has been going on for a long time, and that we have been hit before, and that the conditions which produced those hits have not gone away. But everything we have discussed so far, the supernovae, the iron 60, the kill zone of tens of light years, all of it concerns the ordinary form of stellar death, the explosion that spreads its energy in every direction like a bomb. And as frightening as that is, it is not the worst thing the sky can do, because there is a second, rarer kind of stellar death that does not waste its energy spraying it across the whole sky. It focuses it. It concentrates the entire fury of a dying star into a narrow beam and fires it like a rifle across thousands of light years. The supernova is a bomb. This other thing is a sniper. And while a supernova can only threaten us from within a few tens of light years, this focused weapon can reach across distances vast enough to put a quarter of the entire galaxy within its range. To understand the true statistics of death from stellar explosions, we have to meet the most extreme and concentrated release of energy in the known universe. We have to understand the gamma-ray burst. When astronomers first detected gamma-ray bursts, they had no idea what they were looking at, and the way they found them is a story straight out of the Cold War. In the late 1960s, the United States launched a series of military satellites called the Vela satellites, designed to watch for the gamma-ray flashes that would betray a secret nuclear weapons test in space in violation of the Nuclear Test Ban Treaty. The satellites were looking for human bombs, but starting in 1967, they began detecting flashes of gamma radiation that did not match any nuclear weapon. The flashes were not coming from the Earth. They were not coming from the Sun. They were coming from somewhere out in deep space, brief and intense pulses of the most energetic form of light, appearing at random points across the sky. For years the data was kept classified. When it was finally released in the early 1970s, it announced the discovery of an entirely new and utterly baffling cosmic phenomenon. Something out there was producing flashes of gamma rays so powerful that satellites built to detect nuclear war were picking them up from across the universe. And nobody had any idea what could do that. The mystery deepened for decades. The bursts would appear without warning, flare for anywhere from a fraction of a second to a few minutes, and then vanish, often never to be seen again from the same spot. They came from every direction in the sky, evenly distributed, which was a crucial clue, though a confusing one at first. If they had been concentrated along the plane of the Milky Way, it would have meant they came from within our galaxy, but they were scattered uniformly across the entire sky, which suggested something stranger, something that pointed toward them originating far outside our galaxy, scattered across the whole observable universe. And if they were that far away, then the energy required to make them appear as bright as they did was almost impossible to believe. Here is where the numbers stop making sense in the ordinary way. When astronomers finally measured the distances to gamma-ray bursts in the late 1990s by catching their fading afterglows and pinpointing the galaxies they came from, the truth was almost unbelievable. These bursts were billions of light years away, and to be that far away and still appear that bright, they had to be releasing energy on a scale that dwarfed even the supernova. In the few seconds that a gamma-ray burst is active, it can release as much energy as our Sun will emit over its entire 10 billion year lifetime. Some estimates suggest the most powerful bursts briefly outshine the combined light of every star in the observable universe. For a few seconds, a single dying star becomes the brightest object in all of creation, brighter than everything else combined. But here's the problem, and it is the key to why these things are so terrifying. A gamma-ray burst does not release that energy in all directions. If it did, the energy required would be so absurd that not even the death of a star could supply it. Instead, the burst is beamed. The dying star focuses its energy into two narrow jets, fired in opposite directions out of its poles, like the beams of a lighthouse. This focusing is what makes the energy possible, because the star is not lighting up the whole sky. It is pouring everything into two thin cones, and this beaming has a consequence that is the central, chilling fact of this entire section. A gamma-ray burst is only dangerous if you are standing in the beam. From the side, it is a distant flash, but from directly in front, looking straight down the barrel of one of those jets, the gamma-ray burst becomes the deadliest object in the universe, capable of reaching out and stripping the life from a planet thousands of light years away. But here's what makes this truly terrifying. Unlike a supernova, whose kill zone is measured in tens of light years, a gamma-ray burst aimed directly at Earth could do catastrophic damage from a distance of thousands of light years. The supernova is a threat to our immediate neighborhood. The gamma-ray burst is a threat from across a quarter of the galaxy, and somewhere in that vast region of space, beams like these have been firing at random, in random directions for billions of years. The only question that has ever mattered is whether one of them has ever been pointed at us. And there is a growing, disturbing case that the answer is yes. To see why scientists began to suspect that a gamma-ray burst has already struck Earth, you happen to go back 445 million years to a world that would be almost unrecognizable. There were no plants on land. No animals walked the continents. Life was overwhelmingly an ocean affair, a teeming world of trilobites and brachiopods, of early corals and graptolites and primitive jawless fish, of vast clouds of plankton drifting through warm, shallow seas. This was the Ordovician period, and life had been diversifying for tens of millions of years into one of the richest marine ecosystems the planet had ever seen. And then, in a geological instant, much of it died. The late Ordovician mass extinction was the first of the so-called Big Five, the five greatest mass extinctions in the history of complex life. By most measures, it was the second deadliest of all of them. Something like 85% of marine species vanished. Entire branches of the tree of life were pruned away. It was a catastrophe on a scale that would not be matched until the event that eventually killed the dinosaurs, more than 200 million years later. And for a long time, scientists thought they understood what caused it. The Ordovician extinction coincided with a sudden, severe ice age, a global cooling that locked up the planet's water in ice, dropped sea levels, and destroyed the shallow marine habitats where most life lived. The story seemed clear. The world froze, the seas retreated, and life died. But there was a detail in the fossil record that did not fit, a detail that nagged at certain researchers and would not let go. The pattern of which species died was strange. The organisms that suffered the worst were not randomly distributed. They were concentrated near the surface of the ocean and in shallow waters. The plankton living in the sunlit upper layers, the creatures that floated near the top, were hit catastrophically. But organisms living deeper, in the protected darkness below, fared noticeably better. A simple ice age does not obviously explain that pattern. Cold water does not selectively kill the things near the surface, while sparing the things below. But there is something that does exactly that. Something that comes from above, that strikes the surface of the ocean hardest, that cannot penetrate deep into the water. Radiation. In the early 2000s, the astrophysicist Adrian Melott, working with a team that included specialists in atmospheric chemistry and paleontology, proposed a hypothesis that, at the time, sounded almost outlandish. They suggested that the first pulse of the Ordovician extinction may have been triggered not by anything on Earth at all, but by a gamma-ray burst. A burst originating from a dying star somewhere within about 6,000 light-years of Earth. A beam of gamma radiation that swept across the planet and lasted perhaps only 10 seconds. 10 seconds. A flash shorter than the time it takes to read this sentence aloud, reaching across thousands of light years, with the power to kill a world. Here is the chain of destruction they laid out, and it is worth following carefully, because it reveals exactly how a beam of light from a distant star turns into mass death on a planet. When the gamma rays slam into the upper atmosphere, they do not reach the ground directly. The atmosphere absorbs them, but in absorbing them, the atmosphere is transformed. The radiation rips apart the molecules of nitrogen and oxygen in the air and forces them to recombine into nitrogen oxides, the same brownish toxic compounds found in smog. And these nitrogen oxides are catastrophic for ozone. A single burst lasting just 10 seconds could destroy roughly half of the entire ozone layer almost immediately, and the depletion could persist for years afterward as the chemistry slowly recovered. With half the ozone gone, the sun becomes the executioner. The planet's own star, which had been a source of warmth and life, now floods the surface with ultraviolet radiation that the ozone shield used to block. The increase in harmful ultraviolet light reaching the surface could be many times the normal level, intense enough to cause lethal damage to the DNA of exposed organisms. And this is exactly where the strange extinction pattern finds its explanation. The ultraviolet radiation strikes the surface of the ocean and penetrates only the top layers of water. The plankton and surface-dwelling creatures, exposed and unshielded, are devastated. The deeper organisms, protected by meters of water above them, survive. The fingerprint in the fossils, the selective killing of life near the surface, matches what a gamma-ray burst would do almost perfectly. And the nitrogen oxides do something else too. They are brown. They tint the sky. A heavily affected atmosphere would dim the sunlight reaching the surface, and that dimming could trigger global cooling. The very ice age that scientists had long blamed for the extinction might not have been the root cause at all. It might have been a symptom, a consequence of the gamma-ray burst that came first. The burst poisons the sky. The poisoned sky blocks the sunlight. The blocked sunlight cools the planet, and the cooling drives the glaciation. Under this hypothesis, the gamma-ray burst does not just strip the ozone, it also pulls the trigger on the ice age that finishes the job. One beam of radiation, lasting 10 seconds, setting off a cascade that reshapes an entire planet's climate and erases most of its species. The math is striking. A 10-second event, originating perhaps 6,000 light-years away, reaching across an ocean of space so vast that the light of the explosion travelled for 6,000 years before it arrived, and in the space of those 10 seconds, rewriting the history of life on Earth. The energy involved is so concentrated, so focused, that distance barely protects you. A supernova at 6,000 light-years would be utterly harmless, a faint smudge of light. A gamma-ray burst at the same distance, aimed at you, could be an extinction event. Now, here is where good science demands honesty, and where the story becomes a genuine scientific battle rather than a settled fact. The gamma-ray burst hypothesis for the Ordovician extinction is not proven. It is a hypothesis, and it has serious competition. And this is exactly the kind of conflict that makes the question so compelling, because the experts genuinely disagree, and the evidence is genuinely ambiguous. Before we weigh that disagreement, though, there is a deeper layer to how these explosions kill that we have only touched on, and it makes the threat far more insidious than a simple flash of radiation. Because the danger does not end when the burst does. When a nearby stellar explosion floods Earth with high-energy radiation and cosmic rays, the damage is not confined to the upper atmosphere. The most energetic particles trigger cascades. A single cosmic ray slamming into the top of the atmosphere does not simply stop there. It collides with an air molecule and shatters it, producing a shower of secondary particles, which collide with more molecules and produce more particles. An expanding avalanche racing downward through the air, and at the bottom of that avalanche, reaching all the way down to the surface of the Earth, and even penetrating into the oceans and the soil, are particles called muons. Muons are heavy cousins of the electron, and they are penetrating in a way that ordinary radiation is not. They can pass through hundreds of meters of rock. In an ordinary year, the muons raining down from cosmic rays contribute a small, harmless background dose of radiation that every living thing on Earth absorbs without consequence. But in the aftermath of a nearby supernova, the cosmic ray flux could increase that muon bombardment many times over. And unlike the ultraviolet radiation that only affects the surface, the muons would reach deep. They would penetrate into the water where the deeper sea creatures hide. They would reach burrowing animals underground. They would deliver an elevated radiation dose to nearly everything alive, not for a moment, but potentially for thousands of years, as the cosmic rays from the explosion continued to wash over the solar system. The biological toll would not be a single catastrophic event. it would be a slow, grinding rise in cancers, in mutations, in damaged cells generation after generation across the entire web of the life. This is what makes a nearby supernova so much worse than it first appears. The flash strips the ozone and lets the sun burn the surface. But the lingering cosmic rays poison the whole biosphere from top to bottom for millennia. And the ozone itself does not simply snap back. Atmospheric models suggest that after a severe depletion event, the ozone layer could take years, possibly a decade or more, to fully recover. And during all those years, the surface of the planet would be exposed to a relentless flood of ultraviolet radiation from the sun, damaging plant life, devastating the plankton at the base of the ocean food chain, and propagating that collapse upward through every creature that depends on those organisms to eat. Kill the plankton, and you do not just kill the plankton, you starve everything above them in the food chain. The base of the pyramid collapses, and everything resting on it comes down. This was the second great realization that overturned an earlier assumption. For a long time, scientists who considered the threat of stellar explosions focused mostly on the immediate direct effects, the blast of radiation in the first instant. They thought of it as a single blow. But as the atmospheric chemistry models grew more sophisticated, a different and more frightening picture emerged. The real danger was not the instant of the blow, it was the long aftermath, the years of ultraviolet exposure, the millennia of cosmic ray bombardment, the slow strangulation of the food chain. Everyone had been imagining a punch, when the reality was closer to a poison that lingers in the system long after it is administered. The thing that makes these events lethal is not how hard they hit, but how long the wound stays open. And there is yet another effect that researchers initially underestimated, one that connects the sky to the climate in a way nobody had fully appreciated. The cosmic rays from a nearby supernova do not just damage living tissue. As they cascade through the atmosphere, they ionize the air, and there is evidence that increased ionization can influence the formation of clouds, seeding the tiny droplets around which clouds condense. More cosmic rays could mean more cloud cover, and more cloud cover could mean a cooler planet. This is one of the proposed links between the supernova of 2 to 3 million years ago and the climate shifts of that era, the cooling, the spread of ice, the drying of the African forests. The radiation from a dying star in this picture does not merely irradiate the Earth. It reaches into the machinery of the climate itself and turns the dials, changing the weather of an entire world from hundreds of light years away. Now, here is the crucial point, and it brings us back to the battle over what really killed the Ordovician world. The biggest problem with the gamma-ray burst hypothesis is the nature of the evidence itself. A nearby supernova leaves a fingerprint, the iron 60 we found in the seabed, but a gamma-ray burst from thousands of light years away leaves no such physical trace. It is too far away to deposit radioactive atoms in any detectable quantity, and by the time its faint debris reached us, the telltale isotopes would have decayed to nothing. So there is no smoking gun, there is no layer of gamma-ray burst ash to dig up. The hypothesis rests entirely on the pattern of the extinction, and the way it matches what a burst would theoretically do. It is circumstantial, and in science, circumstantial evidence, however suggestive, is not proof. Many paleontologists favour explanations that stay firmly on Earth. The dominant view, for decades, has been that the Ordovician extinction was driven by the Ice Age and the resulting collapse of sea levels and habitats, processes that need no help from the sky, and more recent research has complicated the picture further. Some studies have pointed to massive volcanism as a key driver, with enormous eruptions pumping gases into the atmosphere, altering the climate and the chemistry of the oceans. There is geochemical evidence, signatures in the rock of volcanic sulfur, that supports an earthbound volcanic cause. Some researchers have even argued that the first pulse of the extinction was caused by volcanic warming and the draining of oxygen from the oceans, the opposite of the cooling that the gamma-ray burst model predicts. The investigators do not agree. The case is open, and this disagreement is not a weakness in the story, it is the heart of it. Because what the Ordovician debate really reveals is something profound and unsettling about our position in the universe. We cannot rule the gamma ray burst out. We know these bursts happen. We know they happen often enough that over the history of the Earth, the planet should have been struck by a dangerously close one, not just once, but several times. The rate estimates suggest that a gamma ray burst close enough to do serious damage to the biosphere should sweep across Earth on average once or twice every billion years. The Earth is 4.5 billion years old. Run the numbers, and the conclusion is inescapable. Even if the Ordovician extinction had a different cause, the Earth has almost certainly been hit by at least one devastating gamma ray burst at some point in its long history. We simply may not have found the body. The crime may have happened, the victims may have died, and the weapon may have left no trace we can still read. And it gets worse when you consider where in the galaxy these bursts are most common and what that means for life beyond Earth. Gamma ray bursts are not evenly distributed in their danger. They tend to come from certain kinds of galaxies and certain kinds of regions, particularly areas where massive stars form and die in great numbers. In our own galaxy, the density of stars increases dramatically toward the center, and when researchers calculated the gamma ray burst danger across the Milky Way, they found something chilling. In the crowded inner regions of the galaxy, within roughly 6,500 light-years of the galactic center, where about a quarter of all the galaxy's stars reside, the odds of a lethal gamma ray burst striking any given planet over the past billion years exceeded 95%. 95%. In the heart of our own galaxy, a planet's chance of having been sterilized by a gamma ray burst is nearly a certainty. The implication is staggering, and it reaches far beyond Earth. It suggests that large regions of the galaxy may be effectively uninhabitable for complex life, not because they lack planets, not because they lack water or warmth, but because they are bathed too frequently in the lethal beams of dying stars. Life there would never get the chance to develop into anything complex before the next burst swept it away and reset the clock. Some scientists have proposed that this defines a kind of habitable zone for the galaxy as a whole, a region far enough from the dangerous, crowded core to escape regular sterilization, but still rich enough in heavy elements to form planets. And our solar system, by this reckoning, sits in a relatively fortunate position, far enough out from the deadly center, in a quiet enough neighborhood for now. It may be that the very location of Earth in the galaxy, our distance from the violent core, is one of the unspoken conditions that allowed life here to survive long enough to become us. There is something else the Iron 60 teaches us, something that turns the abstract statistics into a visceral truth. Across recorded human history, our ancestors witnessed and wrote down a handful of supernovae bright enough to see without instruments. The guest star of 1054 that became the Crab Nebula, a blinding new star in the year 1006, in the constellation Lupus, which may have been the brightest supernova in recorded history, bright enough that some accounts describe being able to read by its light at night. The star Tycho Brahe, measured in 1572, the one Johannes Kepler recorded in 1604, a guest star noted by Chinese astronomers as far back as the year 185. Each of these was the death of a star, and each one was visible because it was relatively nearby in galactic terms, within a few thousand to perhaps 10,000 light-years. Far enough to be harmless, close enough to be seen. And here is the statistical truth hidden in that list. Those visible supernovae, the ones bright enough to startle ancient astronomers, are merely the closest few out of a much larger population. For every supernova close enough and unobscured enough to be seen with the naked eye, many more exploded in the same era, hidden behind the dust of the galaxy. The naked eye supernovae are the tip of an iceberg, and the body of that iceberg is the full rate of stellar death churning through the Milky Way all the time. We see only the nearest, and even those have come close enough, in cosmic terms, to remind us how crowded our corner of the galaxy really is. A supernova at 7,000 light-years lights up our sky. Bring that same explosion to within a few hundred light-years, and it stops being a wonder and becomes a wound. The difference between a beautiful new star and an extinction event is nothing more than where the dying star happened to be standing. And the statistics carry a quiet warning. If our galaxy produces a supernova once or twice every century, and the last one clearly visible from Earth was Kepler's star in 1604. Then more than 400 years have passed without a naked eye galactic supernova. The dust has hidden the others, certainly, but the absence is, statistically speaking, a little overdue. Somewhere in the Milky Way, stars have died in those 4 centuries, their light smothered by intervening clouds. And somewhere, eventually, one will die close enough and clear enough to blaze into our sky again, the first such event since the invention of the telescope, the first that humanity will be able to study with the full power of modern instruments. When it comes, it will almost certainly be far enough away to do no harm. Almost certainly. The statistics favour us, but statistics are not a promise. They are only a description of the odds, and the odds have already been against countless other worlds across the galaxy that happened to be standing too close when their neighbour died. This is the core problem laid bare. The universe is not just capable of killing us, it has been firing on planets throughout the galaxy for billions of years, with supernovae that reach across tens of light years and gamma-ray bursts that reach across thousands. Earth has already been dusted with the ash of nearby supernovae more than once. The Earth sits inside a cavity carved by stellar explosions, and there is a real, serious scientifically defended case that one of the greatest mass extinctions in the planet's history was caused by a beam of radiation from a dying star. The question of death from stellar explosions is not theoretical. It is written in the seabed, in the fossils, in the very structure of the space around us. Before we leave the mechanics of how these explosions kill, it is worth pausing to imagine what a borderline event would actually feel like to the living things caught beneath it, because the statistics become real only when you picture the moment. Imagine a supernova erupting at the very edge of the danger zone, close enough to wound the Earth but not quite close enough to end it. For weeks, that new star blazes overhead, casting hard shadows at midnight, too bright to look at directly, a wound of light in the dark sky. Nothing on the surface feels anything at first. The light is silent, the radiation invisible, but high above, the ozone is already thinning, and over the following months the sunburns begin. Not ordinary sunburns. The ultraviolet flooding through the damaged shield burns exposed skin and eyes, scorches the leaves of plants, and kills the microscopic life drifting near the surface of the seas. The sky may take on a faint brownish tint as nitrogen compounds accumulate. Crops fail, the plankton die, and the creatures that eat the plankton begin to starve, and the dying climbs the food chain one link at a time. There is no single dramatic moment of death. There is only a slow, planet-wide unravelling, stretched across years, set in motion by a flash that lasted weeks and a star that died long before any of it began. That is what the statistics describe. Not an explosion you can dodge, but a slow poisoning of an entire world. And the supernova and the gamma-ray burst are not even the only ways a dead or dying star can reach across space and touch us. There is a third kind of cosmic detonation, and unlike the Ordovician burst, this one happened recently enough that human instruments recorded it directly. It came from a magnetar. A magnetar is one of the strangest objects in the universe, and it is the leftover corpse of a massive star, a neutron star with a magnetic field so powerful it defies comprehension. The magnetic field of a typical magnetar is around a quadrillion times stronger than the Earth's. To put that into something you can feel, a magnetar's field is so intense that if one were positioned as far away as the moon, it would wipe the data from every credit card on the planet and warp the atoms in your body. These objects spin, and occasionally their crusts crack under the unbearable magnetic strain, releasing a sudden violent flare of gamma radiation called a giant flare. And in December of 2004, one of them went off. The source was a magnetar, called by its catalogue designation, sitting roughly 50,000 light-years away, on the far side of our own galaxy, almost as far as you can get, and still be inside the Milky Way. 50,000 light-years is an enormous distance, hundreds of times farther than any star that could threaten us as a supernova. And yet, when that magnetar released its giant flare, the burst of energy was so powerful that even after crossing 50,000 light-years of space, it measurably disturbed the Earth. It struck the upper atmosphere on the night side of the planet, ionized the air, and compressed and rattled Earth's ionosphere. the electrically charged layer of the upper atmosphere. Instruments around the world registered the effect. For a fraction of a second, that flare was brighter in gamma rays than the full moon. From 50,000 light-years away, a dead star reached across the entire galaxy and touched the air above our heads in a way we could measure. Let that sink in. If that same magnetar had been only a few light-years away instead of 50,000, the flare could have done catastrophic damage to the ozone layer in an instant. This is not science fiction. This was recorded. The instruments captured it. The sky measurably struck the Earth within living memory, and the only reason it did no harm is that the source happened to be on the far side of the galaxy. Distance, once again, was the only thing that saved us. And magnetar giant flares are not rare cosmic accidents. They are a known, recurring phenomenon, and there are magnetars scattered throughout the galaxy, any one of which could, in principle, release such a flare. We simply have not had one go off nearby. Yet. There is a fourth way too, discovered only recently, and it ties two of our threats together into something even more violent. When two neutron stars, two of these city-sized stellar corpses, spiral into each other and collide, they merge in a cataclysm called a kilonova. This collision can produce a short gamma-ray burst, a focused beam of radiation just as deadly as the long bursts that come from collapsing massive stars. In the year 2017, astronomers witnessed exactly such a collision for the first time, detecting both the ripples in spacetime it sent out and the burst of light it produced. Two dead stars, slamming together, firing a beam of gamma radiation into space. The universe has more than one trigger finger, and we are only beginning to count them all. And here is a detail about the Iron 60 that should disturb you more than anything else in this section, because it suggests the firing is not safely in the past. When scientists examined fresh Antarctic snow that had fallen within the last 2 decades, they found Iron 60 in it. Not ancient Iron 60 from millions of years ago, but recently deposited atoms. The interpretation is that our solar system is, right now, passing through a region of space still laced with the debris of nearby supernovae, that we are currently drifting through the lingering ash of explosions that shaped our local neighborhood. We are not looking back at a danger that has passed. We are inside the cloud. The dust of dead stars is still falling on the Earth today, settling onto the polar ice, a quiet, continuous reminder that the events we have been describing are not history. They are ongoing. We live in the fallout. What makes all of this so unsettling is not any single fact, but the way they stack on top of one another. Take them one at a time, and each is merely interesting. The kill distance is a number on a chart. The Iron 60 is a curiosity in the seabed. The Ordovician pattern is a debate among specialists. The magnetar flare is a footnote. But stand back and look at them together, and a single picture snaps into focus. We live in a galaxy that fires on its own worlds, constantly, with multiple kinds of weapons, across a range of distances, and the only thing standing between any given planet and catastrophe is the accident of where it happens to sit at the moment a nearby star decides to die. There is no shield we built, there is no force protecting us, there is only distance and luck, and both of those can change. But here's what makes this truly terrifying. Everything we have discussed so far is about the past, about events long finished, about beams that were fired before humans existed. The real question, the one that should keep you watching, is not whether a star has ever killed life on Earth. It is which stars, right now, tonight, are loaded and aimed, because there are specific stars in our sky, with specific names and measured distances that are nearing the end of their lives. Some of them are close. Some of them are massive enough to die in exactly the violent ways we have described. And for at least one of them, scientists spent years genuinely afraid that its poles, and therefore its eventual gamma-ray burst, might be pointed almost directly at us. In the winter of 2019, astronomers around the world began to notice that one of the most familiar stars in the entire night sky was doing something it had never been seen to do. It was fading. The star was Betelgeuse, the bright reddish point that marks the shoulder of the constellation Orion the Hunter, one of the most recognizable stars in the heavens, visible from nearly everywhere on Earth. For as long as humans have watched the sky, Betelgeuse has been one of the dependable beacons of winter, and now, month by month, it was dimming. By the end of 2019 and into early 2020, it had dropped to less than half its normal brightness, the faintest it had been in over a century of careful measurement. To the naked eye, the shape of Orion looked subtly wrong. The hunter's shoulder had dimmed, and among astronomers and the public alike, a single electrifying question spread. Was Betelgeuse about to explode? To understand why that question set off a wave of excitement and dread, you have to understand what Betelgeuse is. It is a red supergiant, one of the largest stars visible to the naked eye, a true monster. If you were to place Betelgeuse where our Sun is, its surface would extend out past the orbit of Mars, swallowing Mercury, Venus, Earth, and Mars whole. It is so large that if you could fly an airplane around its circumference at the speed of a passenger jet, the journey would take thousands of years. And Betelgeuse is old in stellar terms, despite being only a few million years old in absolute terms, because the most massive stars burn through their fuel with reckless speed and die young. Betelgeuse is in the final phase of its life. It is fusing heavier and heavier elements in its core, marching toward the iron that will end it. Astronomers know with certainty that Betelgeuse will explode as a supernova. The only question is when, and the honest answer is that it could be tonight, or it could be 100,000 years from now. So when it dimmed, the hope and the fear was that we were watching the final act, that the great star was about to detonate in our sky, becoming a supernova so close and so bright that it would be visible in daylight, casting shadows at night, rivaling the moon, the most spectacular astronomical event in all of recorded human history. The anticipation was enormous, and underneath the excitement, a quieter question lingered. Betelgeuse sits somewhere between 400 and 700 light-years away. Estimates vary because measuring the distance to such a bloated pulsating star is genuinely difficult. Was that far enough? Was Betelgeuse, this doomed giant, a threat? The investigation that followed was a triumph of modern astronomy, and the answer it produced was reassuring in one way and humbling in another. Astronomers turned every available instrument toward Betelgeuse, including the most powerful telescopes on Earth, and they captured detailed images of the star's surface, something possible for only a handful of stars other than the Sun. And what they found was not the prelude to an explosion. It was something almost mundane, and yet beautiful in its own right. Betelgeuse had belched. The star had ejected an enormous cloud of gas from its surface, a vast plume of material that, as it drifted outward and cooled, condensed into dust. And that dust, hanging in front of the star from our point of view, was simply blocking some of its light. The Great Dimming, as it came to be called, was not a death rattle. It was a giant star sneezing out a cloud of its own substance, temporarily veiling itself behind a curtain of dust. Within months, the dust dispersed, and Betelgeuse brightened back to its normal glory. The hope of witnessing a supernova faded along with the dust, but the episode taught astronomers something valuable, and it carried a sobering reminder. Even our best science cannot precisely predict when a star like Betelgeuse will die. We can read the general signs. We cannot read the exact moment. Betelgeuse will explode, and when it does, it will be one of the most magnificent sights any human has ever seen. But here is the crucial verdict that emerged from all that study. At its distance of several hundred light-years, well outside the kill zone we have discussed, Betelgeuse poses no real danger to Earth. When it finally goes, it will be a spectacle, not a catastrophe. It will brighten our sky, not poison it. The hunter's shoulder will flare into brilliance, blaze for weeks or months, and then fade, leaving behind an expanding cloud and at its heart a newborn neutron star. We will have front-row seats to the death of a giant, close enough to study in extraordinary detail, far enough to survive it unharmed. Betelgeuse is the threat that turned out to be a gift. But if Betelgeuse is the famous false alarm, there is another star that earned a far more sinister reputation, a star that genuinely frightened the scientists who studied it, and whose story is a perfect illustration of how the danger is not just about distance, but about direction. Its name is a catalogue number, Wolf-Rayet 104, and for years it carried a darker nickname, the Death Star. It sits far across the galaxy from us, at a distance that has been notoriously hard to pin down. somewhere in the range of perhaps 8,000 light-years away, though estimates have ranged considerably. At that distance, an ordinary supernova would be completely harmless. But Wolf-Rayet 104 is not an ordinary star, and it does not threaten us with an ordinary supernova. It threatens us with the possibility of a gamma-ray burst, the focus beam, the sniper's bullet, and for a long time, the evidence suggested that the barrel of that gun might be pointed almost directly at Earth. A Wolf-Rayet star is one of the most extreme kinds of star that exists. It is a massive star in the final, furious stage before it dies, having blown away its outer layers of hydrogen to expose its blazing hot inner core, shedding mass in a ferocious stellar wind. Wolf-Rayet 104 is actually a binary, two massive stars locked in orbit, and the interaction of their colliding stellar winds produces something stunning to look at. As the two stars orbit, their winds collide and form dust, and the orbital motion sweeps that dust into a vast spiral, a pinwheel of glowing material winding outward into space. When astronomers first imaged it using a clever technique at the Keck Observatory in Hawaii, the pinwheel shape was breathtaking. But it carried an ominous implication. A pinwheel that is so perfectly circular, so symmetric, when viewed from Earth, suggests that we are looking straight down the axis of the system, straight down at its pole. And the pole is exactly where a gamma-ray burst would erupt. Here was the chain of reasoning that made scientists nervous. Wolf-Rayet stars with rapidly rotating cores are prime candidates to produce long gamma-ray bursts when they finally collapse. Those bursts fire along the star's rotational axis, out of its poles. If we are looking down the pole of Wolf-Rayet 104, as the face-on pinwheel suggested, then when that star eventually dies, its gamma-ray burst could be aimed in our direction. Early analyses estimated that the system's axis was inclined only a small angle away from our line of sight, perhaps within 16 degrees, possibly as little as 12. A gamma-ray burst has a narrow opening angle. If Earth fell within that cone, then across 8,000 light-years of space, the dying Death Star could deliver a blast capable of stripping away a quarter of our ozone layer in an instant, triggering exactly the kind of cascade we saw in the Ordovician scenario. A real star, a real beam, possibly aimed at us. The fear was genuine. Wolf-Rayet 104 was, for years, listed among the most credible natural threats to life on Earth, a loaded gun in the sky with our planet potentially in its sights. The star could explode anytime, from tomorrow to hundreds of thousands of years from now, and because the gamma-ray burst would travel at the speed of light alongside the visible flash, there would be no warning whatsoever. The first sign would be the arrival itself. And then, in a beautiful example of how science self-corrects, the threat dissolved. In the year 2024, the astronomer Grant Hill led a new and far more detailed study of Wolf-Rayet 104, using years of careful spectroscopic observations from the Keck Observatory, the same observatory that had first revealed the pinwheel. By analysing the light of the system in detail, tracking the motion of the two stars as they orbited each other, Hill and his team were able to measure the true tilt of the system's orbit, and the result overturned the old fear. The orbit was not face-on to us after all. It was tilted, inclined by 30 to 40 degrees away from our line of sight. That is a healthy margin. A gamma-ray burst fired along the system's axis would most likely miss the Earth entirely, sweeping past us through empty space. The reprieve came with a fresh mystery, which is so often how astronomy works. If the orbit of the two stars is tilted 30 to 40 degrees away from us, then why does the dust pinwheel appear so perfectly face-on and circular? The spiral and the orbit do not match, and nobody yet fully understands why. As Grant Hill himself reflected, this is exactly how astronomy tends to go. You begin a study, and the universe surprises you with mysteries you did not expect. You answer one question and create two more. The Death Star, it turns out, was probably never aimed at us, but it has not finished surprising us, and it remains one of the strangest and most beautiful doomed systems known. The good news is real. The most famous candidate for a gamma-ray burst aimed at Earth has very likely been disarmed. But the broader lesson cuts the other way. We got lucky with this one. There is no guarantee the next loaded star will be tilted so kindly. If Betelgeuse was the false alarm and Wolf-Rayet 104 was the disarmed weapon, then the next star in our investigation is the one that genuinely deserves to be called a monster, a star so massive and so unstable that it has already tried to explode once and failed. Its name is Eta Carinae, and it is one of the most luminous and most violent stars known in our galaxy. It lies about 7,500 light-years away in the southern sky, and it is not one star but at least two, locked in a tight and turbulent orbit. The primary star is a true behemoth, estimated to be around 100 times the mass of our Sun, possibly more, and shining with the brightness of millions of suns. Stars this massive live fast and die young and violently, and they are perched on a knife edge of stability, so luminous that their own light is constantly trying to blow them apart. Eta Carinae is one of the most massive stars we can study in detail, and it is almost certainly destined to die, not just as a supernova, but possibly as one of the rare, hyper-energetic explosions that could potentially produce a gamma-ray burst. And it has already given us a preview of its violence. In the 1840s, Eta Carinae did something extraordinary. It brightened enormously, becoming for a time the second brightest star in the entire night sky, outshone only by Sirius. This event, which astronomers now call the Great Eruption, was visible to observers across the southern hemisphere and was carefully recorded. For years, the star blazed with unbelievable intensity, and then it faded. What had happened was not a supernova. The star survived. But in that eruption, Eta Carinae ejected an astonishing amount of material, throwing off something like 10 times the mass of our Sun in a single convulsion, an explosion so powerful it would have destroyed almost any other star, and yet Eta Carinae endured. This kind of event is now called a supernova imposter, because it mimics the brightness of a supernova without actually destroying the star. The ejected material is still visible today as a stunning, dumbbell-shaped cloud of gas surrounding the star, two great lobes of glowing debris blasted out in that 19th century paroxysm. We call it the Homunculus Nebula, and it is the shrapnel of an explosion that the star somehow walked away from. The Great Eruption tells us something chilling about Eta Carinae. This is a star so massive and so unstable that it can unleash the energy of a near supernova and survive, which means that when it finally does die for real, the explosion will be on a scale that dwarfs an ordinary supernova. Eta Carinae is exactly the kind of star that could, in principle, produce a gamma-ray burst when it collapses. So the same question that haunted Wolf-Rayet 104 applies here. Is its axis pointed at us? The current understanding is that Eta Carinae's rotational axis, and therefore the direction of any gamma-ray burst it might produce, is not aimed at Earth. The great lobes of the Homunculus Nebula give us a clear sense of the star's orientation, and we appear to be looking at it from the side, not down its poles. That, combined with its considerable distance, means that even Eta Carinae's eventual death is not expected to seriously threaten Earth. It will be a spectacular event, possibly bright enough to be seen in daylight, but most likely not a danger to us. Most likely. Notice how often that phrase appears in this investigation, and notice how much it is being asked to carry. We study these stars, we measure their distances and their orientations, and we conclude again and again that we are probably safe. And in each individual case, the conclusion is sound. But the honest scientist will tell you that our knowledge is incomplete. We do not fully understand exactly how these massive stars die. We cannot predict the precise moment of their deaths. We are still refining our measurements of their distances and orientations, and as Wolf-Rayet 104 showed, those measurements can change dramatically when better data arrives. Each time, the revision happened to bring good news. But the universe was under no obligation to be kind, and the next revision might not be. And there is a deeper unease lurking beneath the survey of these famous giants, because the most dangerous star may not be a famous giant at all. It may be something small, dim, and easily overlooked. This brings us to the fourth member of our investigation, and in some ways the most quietly disturbing, because unlike Betelgeuse or Eta Carinae, this one is not a blazing supergiant that announces its presence. It is a faint, unremarkable point of light, and it is much, much closer than any of the others. Its name is IK Pegasi, and it is the nearest known supernova candidate to Earth. It sits only about 150 light-years away. 150 light-years. Compare that to the 7,500 light-years of Eta Carinae, or the 8,000 of Wolf-Rayet at 104. IK Pegasi is in our backyard by comparison, and it is a binary system with a deadly secret. One of its two stars is a fairly ordinary star, somewhat more massive and hotter than our Sun, but its companion is a white dwarf, the dense, compact ember left behind by a dead star, and it is one of the most massive white dwarfs known, sitting uncomfortably close to the Chandrasekhar limit, the threshold beyond which a white dwarf can no longer support its own weight and detonates as a Type 1a supernova. Here is the scenario that makes IK Pegasi worth watching. Right now, the system is stable, but the more massive of the two ordinary stars is aging, and in the astronomical future, it will swell up into a giant as it nears the end of its life. When it does, it will begin dumping its outer material onto the white dwarf companion. The white dwarf will drink that material, growing heavier and heavier, creeping toward the fatal limit, and if it crosses that line, it will explode in a thermonuclear detonation, a Type 1a supernova, the obliteration of an entire star. The question, once again, is distance. At 150 light-years, IK Pegasi today sits just outside the most pessimistic kill zones, in the range where a supernova could cause real harm to the biosphere, without necessarily sterilizing the planet. But here is the subtlety that makes it so interesting. By the time the white dwarf is actually ready to explode, which will not be for millions of years, the system will have drifted. Stars move. Over millions of years, IK Pegasi will travel a considerable distance through space, and by the time it is ready to die, it will most likely be much farther away than it is now, safely out of range. We happen to be neighbors with a future supernova, but it is a slow-moving neighbor, and it will probably have wandered away before it goes off. Probably. There is that word again. The lesson of IK Pegasi is the one that should stay with you longer than any of the others. The most dangerous stellar bombs are not necessarily the famous, bright, obvious ones. They can be dim, easily missed white dwarfs, quietly drinking from their companions, hiding in plain sight at distances close enough to matter. Astronomers have catalogued the obvious giants, but the full census of white dwarf systems near Earth, the systems that could one day produce a Type 1a supernova, is far from complete. We are reasonably confident there is no immediate threat, but our confidence rests on a survey that is still being conducted, on a map of the local stellar neighborhood that is still being drawn. And that brings us to the final and most important chapter of this investigation. Not a star, but the human effort to find them all, to map the threats, and to build against all odds something like an early warning system for the death of stars. Because if there is one thing this entire survey has taught us, it is that our safety depends entirely on knowledge. The only defense against a dying star is to know where they are, how far away, and which way they are pointed. And so, over the past few decades, astronomers have been quietly assembling the tools to do exactly that. The first piece of that effort is the hunt for the threats themselves, the systematic survey of every nearby star capable of dying violently. Astronomers have been cataloguing the massive stars within 1,000 light-years, mapping the Wolf-Rayet stars, the supergiants, the white dwarf binaries, measuring their distances with ever-increasing precision. A European space mission called Gaia has been particularly transformative, measuring the precise positions and distances of more than 1 billion stars in our galaxy, building the most detailed three-dimensional map of the Milky Way ever assembled. With Gaia's data, astronomers can finally place the nearby stars in accurate three-dimensional space, refining exactly which ones lie inside the various danger zones and which lie safely beyond. The reassuring headline from all this work has held steady. There is no known star within the immediate supernova kill zone of roughly 50 light-years. The nearest candidates, like IK Pegasi, sit beyond the most dangerous range, but the survey continues because the map is never quite finished and because the dim, hidden white dwarf systems are the hardest to find. The second piece is stranger and more remarkable, and it harks all the way back to supernova 1987A and those 24 neutrinos. Remember that the death of a massive star releases its energy first, as a flood of neutrinos, hours before the visible light arrives. Astronomers realized that this delay, though brief, could serve as a warning, so they built a system to exploit it. It is called the Supernova Early Warning System, and it links together neutrino detectors around the world into a single network. If a massive star in our galaxy collapses, the burst of neutrinos will reach Earth and pass through these detectors. And if multiple detectors register the same burst at the same moment, the system can automatically issue an alert, telling astronomers across the planet that a supernova has just occurred and that the light is about to arrive. It is, in effect, a tripwire strung across the galaxy, sensitive to the ghostly first whisper of a dying star. The warning it provides is measured in hours, not years, and it would not help us defend against a truly dangerous nearby explosion, because for that, hours of warning would be far too little to matter, but it represents something profound about the human response to these threats. We cannot stop a star from dying. We cannot deflect a gamma-ray burst or shield the planet from a nearby supernova. Our entire defense, for now, consists of knowledge and attention, of watching the sky carefully enough to understand the dangers, even when we are powerless to prevent them. The Supernova Early Warning System is a tripwire for an attack we cannot block. But it is also a statement of intent, a declaration that we will at least see it coming, that we will not be caught entirely unaware. The numbers are striking when you consider what these efforts have collectively established. After decades of surveying, the consensus is clear and, for now, comforting. The Earth is not under immediate threat from any known star. There is no supernova primed to go off within the deadly radius. The most famous candidate for a gamma-ray burst aimed at us has very likely been shown to miss. The nearest future supernova will probably have drifted to a safe distance before it explodes. By every measure we can currently make, we are safe right now in this moment of cosmic time. And yet every one of those reassurances carries a quiet asterisk, a probably, a most likely, a by every measure we can currently make. The safety is real, but it is the safety of good odds, not the safety of a guarantee. It is the safety of a planet that has, so far, been standing in the right place at the right time. And it gets worse the longer the timescale you consider, because over millions of years, the right place does not stay the right place. The solar system keeps moving, keeps drifting toward the star-forming regions of the Orion Arm, keeps rolling the dice. The surveys tell us we are safe for now, for the next thousands or even tens of thousands of years. They cannot tell us we are safe for the next 10 million. On those timescales, the statistics reassert themselves, and the statistics say that, given enough time, our number will eventually come up, just as it has come up for countless worlds across the galaxy already. The investigation into the named stars ends not with a clean all clear, but with a more honest and more haunting verdict. We are safe today. We are probably safe for a long time. But we live in a galaxy that does not stop firing, and we are not standing still. There is one more place we have to look before this investigation is complete, and it is not a single star, but an entire neighborhood of them, the most likely birthplace of the next nearby threat, and quite possibly the source of the explosions that already dusted our planet with Iron 60. It is called the Scorpius-Centaurus Association, and it is the closest large group of massive young stars to the Sun. A stellar association is a loose cluster of stars that were all born together from the same vast cloud of gas, and the massive ones among them are destined to die together in a sequence of supernovae spread across a few million years. The Scorpius-Centaurus Association lies a few hundred light-years away, and it contains many massive stars, the kind that end their lives in core collapse. Over the past several million years, this association has very likely been the source of multiple nearby supernovae, the same explosions that carved the local bubble we live inside and rained Iron 60 onto the Earth and the Moon. In a real sense, the Scorpius-Centaurus Association has already fired on us, repeatedly, and we carry the radioactive evidence in our seabeds. And it is not finished. The association still contains massive stars that have not yet died, stars that will, over the coming millions of years, explode as supernovae. The good news is that most of them are currently far enough away, several hundred light years, that their deaths would wound the biosphere rather than sterilize it. But this is the neighborhood to watch. As the solar system continues its drift through the galaxy, and as the stars of Scorpius-Centaurus continue their own motions, the geometry will keep shifting. This is where the statistics live. not in any single doomed star, but in a whole population of them, ticking down toward their deaths a few hundred light years from our world, in the closest stellar killing ground to home. There is a category of threat that all of our surveys and warning systems struggle to address, and it deserves its own moment, because it is the one that keeps the most careful scientists honest. It is the threat we cannot see coming, the hidden gun in a sky we have only partly mapped. Consider the limits of what we actually know. Our census of the dangerous stars near Earth is impressive but incomplete. The bright supergiants like Betelgeuse and the luminous monsters like Eta Carinae announce themselves. They are easy to find and easy to study. But the white dwarf binaries, the systems that produce Type 1a supernovae, are dim and unremarkable, and many of them have surely escaped our catalogues. There could, in principle, be a white dwarf quietly approaching its fatal limit somewhere closer than we realize, hidden in the glare of a brighter companion, or simply too faint to have drawn attention. We believe there is no such immediate threat within the kill zone, and the evidence supports that belief. But belief built on an incomplete survey is not the same as certainty, and there is an even subtler danger, the runaway star. The galaxy is full of stars that have been flung out of their birth clusters by gravitational interactions or by the explosions of their former companions, and these stars travel through space at enormous speeds, tens or even hundreds of kilometers per second. A massive runaway star could, over time, wander into our neighborhood from somewhere else entirely, a doomed giant arriving from a distant part of the galaxy, ticking down toward its own death as it approaches. We map the stars where they are now, but the map is a snapshot of a galaxy in constant motion, and the dangerous stars do not always stay where we last saw them. The threat that eventually finds Earth, millions of years from now, may be a star that is not currently anywhere near us, a wanderer still on its way. This is the deepest source of unease in the entire science of stellar threats. It is not that we have found a loaded gun pointed at Earth. We have not. It is that our ability to find every possible gun is limited, and the sky is vast, and the stars move, and the timescales over which the danger plays out are so long that the galaxy will rearrange itself many times over before our number comes up. The surveys reassure us about the present. They cannot fully reassure us about the deep future, because the deep future depends on stars and motions we have not yet measured, and on deaths that have not yet been triggered. What would we even do if a survey did one day reveal a genuine threat, a nearby star primed to die within the kill zone and aimed our way? The unsettling answer is that, with anything resembling current or near-future technology, we would do nothing, because there is nothing to be done. You cannot evacuate a planet's worth of life. You cannot build a shield around an entire world to stop a flood of gamma rays and cosmic rays. You cannot push a star off its course or delay its collapse. The most a future civilization might do is take shelter, retreating underground or beneath the oceans, where rock and water could absorb some of the radiation and ride out the worst of the ultraviolet years that followed. Deep enough underground, complex life might survive even a severe ozone collapse, waiting out the decade or more it would take the atmosphere to heal. This is in fact part of why mass extinctions are rarely total. Something always survives in the protected places, in the deep ocean, in the soil, in the dark. Life is harder to erase completely than it is to devastate. But that is survival, not defense. It is enduring the blow, not preventing it. And it underscores the strange and humbling lesson at the center of this entire investigation. We have become a species capable of mapping the galaxy, of measuring the distances to dying stars, of simulating the destruction of our own atmosphere molecule by molecule, of building tripwires sensitive to ghost particles from across the Milky Way. We understand the threat in extraordinary detail, and against the threat itself, all of that understanding gives us nothing but the ability to watch it arrive and the wisdom to hide from its aftermath. Knowledge in this one domain does not equal power, it equals awareness, and awareness perhaps is its own kind of dignity, even when it cannot save us. There is one explosion we have not yet examined in the detail it deserves, even though it has taught us more about stellar death than any other, and it is worth returning to before we count the odds. Supernova 1987A, the death of that massive star in the Large Magellanic Cloud, became the most intensively studied supernova in history. And for nearly 4 decades, astronomers have watched its aftermath unfold in real time, like forensic investigators studying a crime scene that keeps revealing new clues. When that star exploded, it was the first supernova in centuries close enough to study with modern instruments, and it confirmed, validated, or overturned an enormous range of theories about how stars die. The neutrino burst confirmed that core collapse really is, first and foremost, a neutrino event, exactly as the models had predicted. The expanding debris let astronomers watch the radioactive elements forged in the explosion decay away, glowing as they did so, confirming that supernovae are indeed where many of the universe's heavy atoms are manufactured. The shockwave, racing outward, eventually slammed into a ring of gas the star had shed before it died, lighting up that ring like a string of cosmic pearls, a glowing necklace that has been photographed and studied for decades. Every stage of the aftermath was a test of our understanding, and over, the predictions held. But one piece of the puzzle remained stubbornly missing, and it gnawed at astronomers for more than 30 years. The theory said that, when a massive star collapses, it should leave behind a compact remnant at its heart, either a neutron star or, for the most massive stars, a black hole. For supernova 1987A, the expectation was a neutron star, a city-sized ball of ultra-dense matter, the crushed core of the dead giant. But for decades, no one could find it. Astronomers searched the wreckage and saw nothing. The remnant, if it existed, was hidden behind the thick dust of the explosion. Some began to wonder whether it had collapsed all the way into a black hole after all, or whether something stranger had happened. The missing neutron star became one of the great open questions surrounding the most famous supernova of the modern age. And then, recently, using the extraordinary infrared vision of the James Webb Space Telescope, the most powerful space observatory ever built, astronomers finally found it. Peering through the dust with the telescope's infrared eyes, they detected the unmistakable signature of a neutron star buried at the heart of the wreckage, exactly where the theory had said it should be. After more than 30 years of searching, the crushed corpse of the star was confirmed, glowing faintly in the depths of its own debris. The prediction had been right all along. The star died, its core collapsed into a neutron star, and now, decades later, we can finally see the body. It was a triumph that closed a chapter astronomers had been writing for a generation. And it stands as a reminder of how patient this science must be, how a single stellar death can be studied for 40 years and still surprise us. Supernova 1987A matters to our story because it is the Rosetta Stone of stellar death, the one nearby example that let us check our theories against reality. Everything we believe about what a closer, more dangerous supernova would do to Earth rests on the foundation that events like 1987A confirmed. And that brings us to one of the most chilling exercises in all of this science. Scientists have not only calculated how close a supernova would have to be to harm us, they have built detailed computer models simulating exactly what would happen to the Earth's atmosphere, step by step, if one went off inside the kill zone. These simulations are grimly specific. Researchers like Brian Thomas and Adrian Mellott have run atmospheric chemistry models that trace, hour by hour and year by year, what a nearby supernova or gamma ray burst would do to our air. They model the gamma rays striking the upper atmosphere, the formation of the nitrogen oxides, the destruction of the ozone, the years-long depletion that follows, and the resulting flood of ultraviolet radiation reaching the surface. They calculate how much the ozone would be reduced at various distances and how long it would take to recover. They estimate the increase in ultraviolet radiation and the corresponding increase in DNA damage to living things, and the results are sobering. For a gamma ray burst at a few thousand light-years aimed at Earth, the models predict ozone depletion severe enough to roughly double or more the damaging ultraviolet radiation reaching the surface, sustained for years, with catastrophic consequences for the base of the food chain. For a supernova within the kill zone, the picture is worse. The math is striking precisely because it is so detailed. This is not vague hand-waving about cosmic danger. These are quantitative predictions, modelled molecule by molecule, of how a dying star dismantles the shield that keeps a planet alive. What makes these modelling efforts so valuable is that they let us understand a threat we have, thankfully, never directly experienced in recorded history. We have never watched a kill-zone supernova destroy the ozone layer, but we can simulate it, drawing on everything we learned from events like 1987A, from the atmospheric chemistry we understand in detail, and from the geological evidence of past events. The simulations are how we turn the abstract danger into concrete numbers, how we draw the kill zone with confidence, how we know that 50 light-years is roughly where catastrophe begins. They are the bridge between the death of a distant star and the survival of life on Earth. So now, armed with the lessons of 1987A and the predictions of these models, let us finally put real numbers on the statistics of death, because the title of this story is a promise, and the promise deserves to be kept. How likely is it actually that a stellar explosion will kill you, or your descendants, or end civilization? The honest answer requires separating timescales, because the danger looks completely different depending on how far into the future you look. On the scale of a single human life, the risk is essentially zero. There is no known star poised to explode within the kill zone in the next several decades, or even the next several thousand years. You will almost certainly never witness a dangerous nearby supernova. If you are extraordinarily lucky, you might witness a safe, beautiful one, like the eventual death of Betelgeuse, a spectacle rather than a threat. On the scale of a human lifetime, death from a stellar explosion is one of the least likely ways for you to die. The numbers are reassuring, and they should be stated plainly, because fear without proportion is its own kind of error. But stretch the time scale, and the picture darkens. Consider the entire future of human civilization, however long that may last. A dangerously close supernova within the 30 to 50 light-year kill zone is estimated to occur near Earth roughly once every few 100 million years. A devastating gamma-ray burst sweeping across the planet is estimated at perhaps once or twice every billion years. These sound like comfortingly long intervals. But they are not zero, and over the immense spans of geological time, they accumulate into near certainties. The math is striking when you frame it this way. If a civilization could somehow endure for tens of millions of years, it would face a real and growing probability of encountering one of these events. Over the 4.5 billion years Earth has existed, the planet has almost certainly been struck by dangerous explosions multiple times. The Iron 60 proves the near misses. The Ordovician extinction may prove a direct hit. We are not asking whether these events happen to planets like ours. We know they do. We are only asking when the next one finds us. Now compare this to the other great natural threats to life on Earth, because context is everything. The asteroid impact that ended the age of the dinosaurs is the most famous extinction event, and large impacts capable of global devastation are thought to occur on the scale of once every 100 million years or so. Massive volcanic events, the kind that flood entire continents in lava and poison the atmosphere, occur on roughly similar timescales, and have been linked to several of the great mass extinctions. The stellar explosion sits right alongside these as a member of the same grim family. It is not the most frequent threat. The asteroid and the volcano are probably more likely to be the cause of any given future catastrophe. But the stellar explosion is unique among them in one terrible respect. There is absolutely nothing we could do about it. Consider that asymmetry, because it is the heart of why these events frighten the scientists who study them. An incoming asteroid can, in principle, be detected years or decades in advance, tracked and potentially deflected. Humanity has already tested the ability to nudge an asteroid's path. A volcanic supereruption gives geological warning signs, swelling ground and rising tremors that might offer time to prepare. But a nearby supernova or a gamma-ray burst offers none of this. The radiation travels at the speed of light, which means the warning and the event are the same thing. There is no detecting it in advance, because nothing travels faster than the light that carries the news of its own arrival. There is no deflecting a beam of gamma rays. There is no shield we could build, no bunker deep enough to protect an entire biosphere, no technology even conceivable with current physics that could stop it. Against the death of a nearby star, the most advanced civilization imaginable would be exactly as helpless as the trilobites of the Ordovician seas. We could see the threats coming over millions of years, mapping the doomed stars. But in the final moment, we could only watch. This is the uncomfortable truth that the statistics deliver. The probability of death from a stellar explosion is low on any timescale a human cares about, but it is not zero on the timescale of a species, and it climbs towards certainty on the timescale of a planet. And it is the one cosmic catastrophe against which knowledge buys us understanding, but not protection. We can know exactly how we might die, and still be unable to prevent it. That is a strange and humbling position for a species that prides itself on solving its problems. And yet, against this grim accounting, science continues to push back the only way it can, by learning more. In recent years, a new generation of telescopes and surveys has transformed our ability to study stellar explosions, not to stop them, but to understand them with a precision that would have been unimaginable a generation ago. Automated survey telescopes now scan the entire night sky repeatedly, comparing each image to the last, watching for any point of light that suddenly brightens. These surveys discover thousands of supernovae every year, mostly in distant galaxies, building an enormous statistical catalogue of stellar death. Every supernova they find, even a faint 1 billions of light-years away, sharpens our understanding of how often these explosions happen, how powerful they are, and how dangerous they could be to a planet caught nearby. A powerful new observatory, built in the mountains of Chile and equipped with the largest digital camera ever constructed for astronomy, has begun an unprecedented survey of the entire southern sky, imaging it again and again over years, catching transient events of every kind, including supernovae, in numbers never before possible. The flood of data from these efforts is revolutionizing the study of stellar death. We are, for the first time, building a true statistical census of how stars die across the universe, which in turn refines our estimates of the danger to Earth. Each new supernova caught in a distant galaxy is another data point in the grim actuarial table of cosmic risk, another measurement that tightens the numbers on exactly how often and exactly how close these events occur. And there is a deeper purpose to all this watching, beyond calculating the odds of our own demise. By studying stellar explosions, we are studying the engines that built the universe we live in, because here is the thread that has been running quietly beneath this entire investigation, the thread we have touched, but never fully pulled. Every supernova we catalogue, every gamma-ray burst we measure, every dying star we map is not just a potential threat, it is a factory. These explosions are where the universe makes the very atoms that life is built from. And that fact is about to transform this entire story from one about death into one about creation. Because the line between the two is far thinner and far stranger than anyone watching a star explode would ever guess. Which leads to the deepest truth of all, the one this entire story has been building toward. The revelation that turns everything we have learned about the danger of dying stars completely inside out. Because the same explosions that threaten to end us are the explosions that made us. And once you understand that, you can never look at a supernova or at your own hands the same way again. So let us pull that thread now, all the way, and see where it leads. We have spent this entire journey treating stellar explosions as executioners. We have measured their kill zones, charted their beams, counted the species they may have erased, and calculated the odds that one of them will, someday, come for us. And every number we found pointed in the same grim direction, toward danger, toward extinction, toward death, falling out of a clear night sky. But there is a problem with that picture, a problem so fundamental that it should make you stop and reconsider everything. Because if stellar explosions are nothing but agents of death, then there is a question no one has been able to answer. Where did you come from? Not you, the person, with your name and your history. You, the physical object. The roughly 7 octillion atoms that make up your body. The iron riding in your blood. The calcium locked in your bones. The oxygen filling your lungs right now as you breathe. The carbon forming the backbone of every protein and every strand of your genetic code. Where did those atoms come from? Trace them back far enough, and you arrive at an answer that should feel impossible. Almost every one of them was made inside a star, and almost every one of them was scattered into space by a star's violent death. The very explosions we have spent this whole story fearing are the explosions that built the raw material of life itself. Something is wrong with our assumptions, profoundly wrong, because we have been looking at these events as the end of things, when they are just as truly the beginning. Let that sink in. The thing that can kill you is the same thing that made you. To understand how that can possibly be true, we have to go back, all the way back, to the very beginning of everything. When the universe was born, in the event we call the Big Bang, it was almost unimaginably simple. As the infant cosmos expanded and cooled in its first few minutes, it forged the lightest elements out of pure energy. The result was a universe made of roughly 3/4 hydrogen and 1/4 helium, with the faintest trace of lithium, the third element, and essentially nothing else. That was the entire inventory of creation. No carbon, no oxygen, no nitrogen, no iron, no calcium, no phosphorus, no sodium, none of the elements that life requires, none of the elements that rock and metal and water require. The early universe was a vast, dark ocean of the two simplest gases, and nothing more. A universe like that cannot build planets. It cannot build chemistry. It certainly cannot build biology. If the cosmos had stayed that way, it would have remained forever empty, a sterile fog of hydrogen drifting in the dark. So the obvious question is, what changed? Where did all the other elements, the 90 or so heavier kinds of atoms that make up worlds and water and living things, actually come from? The answer is that they were cooked, one by one, in the hearts of stars. A star is, at its core, a fusion furnace. The crushing pressure at its center forces hydrogen nuclei to slam together and fuse into helium, releasing the energy that makes the star shine. For most of a star's life, that is all it does, patiently turning hydrogen into helium across millions or billions of years. But when a massive star begins to run low on hydrogen fuel in its core, something remarkable happens. The core contracts, grows hotter, and begins to fuse the helium ash into heavier things, into carbon and oxygen. And when the helium runs low, if the star is massive enough, the process repeats again and again, each stage burning the ashes of the last. Carbon and oxygen fuse into neon and magnesium. Those fuse into silicon and sulfur, and silicon, in the final desperate days of a dying giant, fuses into iron. The star becomes a vast cosmic onion, layer upon layer of progressively heavier elements, each shell wrapped around the one below it, with a growing core of iron at the very center. The factory of creation is running at full capacity, building the periodic table from the inside out. But here is where the story turns, and where the deep connection between life and death reveals itself. Iron is the end of the line. Iron is the most tightly bound nucleus in all of nature, the most stable arrangement of protons and neutrons that exists. When a star fuses lighter elements together, the reaction releases energy, which is what holds the star up against its own gravity. But to fuse iron into anything heavier does not release energy. It consumes energy. The moment a massive star builds a core of iron, its furnace can no longer push back against gravity, because the next reaction would steal energy rather than supply it. And so, as we have already seen, the core collapses and the star detonates. The very element that life depends upon most intimately, the iron in your blood that carries oxygen to every cell in your body, is the element whose creation kills the star that makes it. Death is not a side effect of this process. Death is the mechanism. The star must die to release what it has built, because think about what that explosion actually does. For the entire life of the star, all those precious elements, the carbon and oxygen and iron, are locked away inside it, buried under crushing layers, doing nothing, useful to no one. A star could forge a planet's worth of carbon and never share a single atom of it with the universe. The elements need to get out, and the only way out for most of them is the explosion. The supernova is not just an act of destruction, it is an act of distribution. In the span of seconds, the dying star blasts everything it has spent its life building out into space, hurling carbon and oxygen and silicon and iron across light years at thousands of kilometers per second, seeding the surrounding darkness with the ingredients of worlds. This is not science fiction, and it is not metaphor. It is the literal, physical history of every atom heavier than helium that you have ever touched, eaten, or been made of. Each one rode out of a dying star on the shockwave of a supernova. And the supernova does something even more astonishing in its final moments, something that explains where the rarest and most valuable elements of all came from. We said that fusion stops at iron, that nothing heavier can be built by the ordinary burning of a star. So how does the universe contain gold? How does it contain silver, platinum, uranium, the heavy elements that have shaped human history and that sit in tiny quantities, even within your own body? The answer lies in the explosion itself and in an even more violent cousin of it, in the chaos of a supernova, and especially in the unimaginably extreme collision of two neutron stars, the kind of event we touched on earlier. Matter is bathed in a flood of free neutrons so dense that atomic nuclei capture them faster than they can decay. This is the rapid neutron capture process, and in a matter of seconds it builds the heaviest elements in nature, racing up the periodic table to gold, to platinum, to uranium and beyond. When two neutron stars merged and astronomers caught the light of that collision, they measured the signature of newly forged gold and other heavy metals being flung into space in quantities equal to many times the mass of the Earth. Every gold ring that has ever been exchanged, every gold coin that has ever been minted, every atom of gold in every vault and every piece of jewellery on this planet was made in the death throes of stars and the collisions of their corpses billions of years before the Earth existed. We did not mine our gold from the Earth so much as the Earth inherited it from the sky. So now assemble the whole picture, because it is staggering. Around 4.5 billion years ago, in an unremarkable corner of an ordinary galaxy, a vast cloud of gas and dust began to collapse under its own gravity to form our Sun and its planets. But that cloud was not made of pristine Big Bang hydrogen. It was enriched, seeded, polluted in the most life-giving way possible, with the scattered ashes of countless stars that had lived and died before our Sun was ever born. The carbon in that cloud had been forged in some ancient red giant. The oxygen had been cooked in the core of some massive star that exploded perhaps hundreds of millions of years earlier. The iron had been built in the final hours of a supernova. The gold and the uranium had been hammered into existence in a neutron star collision somewhere across the galaxy. Our entire solar system, the earth beneath your feet, the water in the oceans, the air in the sky, and every living thing that has ever crawled or swum or flown or thought was assembled out of the recycled remains of dead stars. We are, quite literally, the children of stellar catastrophe. Carl Sagan put it in words that have never been improved upon when he said that we are made of star stuff. But it is worth being precise about just how literally true that is, because it is easy to hear a phrase like that and treat it as poetry, as a pretty sentiment with no real weight. It is not poetry. It is forensic fact, as solid as the iron in the blood that is, at this very moment, carrying oxygen from your lungs to your brain so that you can understand these words. That iron is older than the sun. It was made inside a star that died before the Earth existed, in an explosion of the exact kind we have spent this entire story learning to fear. The calcium that gives your bones their strength was made the same way. The phosphorus that forms the backbone of your genetic code. The sodium and potassium that fire every thought and every heartbeat. The oxygen that fills every breath. All of it was forged in stars and freed by their deaths. You are not merely related to the cosmos. You are not merely connected to it. You are it. You are a piece of the universe that has been assembled temporarily into something that can look up at the sky and recognize where it came from. And this transforms the meaning of everything we have learned. Every supernova we mapped as a threat, we can now see as an ancestor. Every gamma-ray burst we measured as a weapon, we can now see as a forge. The local bubble we live inside, that cavity blown clear by the supernovae of the Scorpius-Centaurus Association, is not just a region scoured by stellar violence. It is a graveyard, yes, but it is also a nursery, salted with the heavy elements of the very stars that died to create it. The Iron 60 raining gently into the Antarctic snow, the radioactive fingerprint of supernovae that exploded near us within the last few million years, is not just evidence of how close we came to disaster. It is a delivery. It is the universe, even now, still sending us pieces of dead stars, still topping off the cosmic inheritance that built us. The same nearby explosions that may have scorched our ozone and nudged our climate and pressured our ancestors to evolve were also, in the deepest sense, simply the latest installment in the 4 billion year process that made us possible in the first place. To feel the full weight of this, follow a single atom. Pick one of the iron atoms in your blood, one of the countless trillions riding inside your red blood cells at this very moment. Trace its history backward. Before it was in you, it was in your food, in the soil, in the rock and water of the earth. Before that, it was part of the spinning disk of dust and gas that collapsed to form the earth itself, more than 4.5 billion years ago. Before that, it drifted for untold ages through the cold and empty reaches of interstellar space, one speck among uncountable others, part of a vast cloud waiting in the dark. And before that, before all of it, that single atom of iron was hurled outward at thousands of kilometers per second on the shockwave of a dying star, in an explosion so bright it briefly outshone 100 billion suns. That atom witnessed the death of a star. It was born in that death. It carries, encoded in its very existence, the memory of one of the most violent events the universe can produce. And now it sits quietly inside you, doing the gentle, patient work of keeping you alive, ferrying oxygen breath by breath, year after year, as if it had never known anything but peace. Every atom in your body has a story like that. Every one of them is a survivor of a cosmic catastrophe, a piece of shrapnel from an ancient explosion, repurposed across billions of years into the machinery of a living, thinking being. You are not standing apart from the violence of the universe, observing it safely from a distance. You are made of it. You are what the violence becomes when enough time passes and enough stars have died. And the recycling does not stop with you. The atoms that make you now were borrowed, not given. They passed through the earth and the oceans and the bodies of countless creatures before they reached you. And when you are gone, they will move on again, into the soil, into other living things, into the long, slow circulation of matter that has been running since the earth was young. On the grandest scale, even our own sun will one day return what it has built. Billions of years from now, when it exhausts its fuel, it will not explode as a supernova, because it is not massive enough. Instead, it will swell into a red giant, shed its outer layers gently into space as a glowing shell called a planetary nebula, and leave behind a slowly cooling ember. But in that shedding, it too will scatter the carbon and oxygen it forged across its lifetime, seeding the galaxy with a little more of the raw material of future worlds. The cycle that made us will go on making things long after we are gone, an endless turning of stellar death into the possibility of new life. We are not the final product of this process. We are one passing moment in a recycling of matter that has no end in sight. This is the revelation that turns the entire story inside out. We began by asking how likely it is that a stellar explosion will kill us, and that is a real question, with real and sometimes frightening answers, as we have seen. But it is only half the question, and arguably the smaller half, because the full truth is that stellar explosions are not the enemy of life. They are its precondition. A universe gentle enough never to produce a supernova would be a universe forever trapped in hydrogen and helium. A universe that could never build a planet, never assemble a cell, never give rise to a single living thing capable of fearing the dark. The violence is not a flaw in the cosmos that life must survive despite. The violence is the engine that made life possible at all. We owe our existence to the very catastrophes we have learned to dread. And that paradox, that unbearable and beautiful paradox, is the real statistics of death from stellar explosions. The numbers do not only measure how the universe might end us, they measure how the universe made us. The same equation runs both ways. Once you accept that stellar explosions are both the destroyers and the creators of life, a far stranger and more profound set of questions opens up. Because if the same violence that builds the atoms of life can also sterilize a planet, then the universe is playing a delicate balancing act, and the conditions under which life can actually take hold and survive long enough to matter become a razor's edge. And when you start to map that razor's edge across the galaxy, you discover something that should change how you think about our place in it. We may not just be lucky to be alive. We may be lucky to live exactly where we do, and exactly when we do, in a way that is far from guaranteed for most of the universe. Consider first the question of where. We have spent this story talking about individual threats, the particular star that might explode, the specific beam that might sweep across us. But step back and look at the galaxy as a whole, and a pattern emerges. The center of the Milky Way is a dense, crowded, violent place. Stars are packed tightly together there, supernovae go off far more frequently, gamma-ray bursts are more common, and the radiation environment is, by the standards of life, relentlessly hostile. We saw earlier that within a certain distance of the galactic core, the statistical likelihood of being caught by a lethal burst over the span of 1 billion years approaches near certainty. A planet in that region might form just fine, might even develop the early stirrings of life, but it would face a cosmic bombardment so frequent that complex, advanced life would struggle to ever get a foothold, repeatedly knocked back to the starting line by catastrophe after catastrophe. The crowded inner galaxy may be a place where life is regularly born and regularly exterminated, never given the long stretches of calm it needs to become anything ambitious. But now go the other way, out to the sparse and lonely outer edges of the galaxy, far from the crowded core. The radiation danger drops dramatically out there, the supernovae are rare, the bursts are distant. It sounds safer, and in one sense it is. But there is a different problem, and it connects directly to everything we just learned about where atoms come from. The outer reaches of the galaxy are poor in heavy elements. There have been fewer generations of stars out there to forge and scatter the carbon, oxygen, iron, and the rest. A region starved of those elements is a region that struggles to build rocky planets at all, let alone the rich chemistry that life requires. So the far suburbs of the galaxy may be calm, but they may also be barren, lacking the very stellar ashes that make planets and biology possible. Too close to the core, and life is repeatedly sterilized by violence. Too far out, and life lacks the raw materials to begin. And somewhere in between lies a band, a ring, a sweet spot, where the heavy elements are abundant enough to build worlds, but the radiation is sparse enough to let life endure. Astronomers call it the galactic habitable zone, and our solar system sits squarely, comfortably, almost suspiciously well within it. Let that sink in, because it reframes our entire situation. We are not just at a safe distance from the nearest dangerous star, though we are. We are not just shielded for the moment by the empty local bubble, though we are. We are positioned, on the largest scale, in one of the relatively narrow regions of the entire galaxy, where the long, uninterrupted flourishing of complex life is even possible. Closer in, and we would have been cooked. Further out, and we might never have formed at all. Our cosmic address is, by the standards of the wider galaxy, remarkably privileged, and there is no reason we earned it. We simply happen to coalesce in the right place, in a galaxy where most places are, for one reason or the other, far less hospitable. Now consider the question of when, because it turns out to be just as important as where, and even more startling. The universe is roughly 14 billion years old. Our solar system is about 4.5 billion years old. So we arrived when the universe was already most of the way through its current age. Why so late? Why not sooner? Part of the answer is the one we have already uncovered. The early universe simply did not contain the elements that life requires. It took generations of stars, living and dying, and enriching the cosmos with their ashes, to build up enough heavy elements for planets like Earth to form. The first stars were made of nearly pure hydrogen and helium, and they had no rocky planets, because there was nothing to make rocks out of. Only after those first stars died, and the next generation died, and the one after that, did the galaxy accumulate enough carbon and oxygen and iron to assemble a world like ours. Life had to wait for the universe to grow rich enough to support it. We are late arrivals not by accident but by necessity. The cosmos had to age before it could give birth to us. But there is a second part to the answer of when, and it is more unsettling. The early universe was not just poor in elements, it was also far more violent. Galaxies were smaller and more crowded, they collided and merged more often. Star formation raged at a furious pace, and with all that frenzied star formation came supernovae and gamma-ray bursts at rates far higher than today. Some scientists have proposed a genuinely sobering idea that for much of cosmic history, large fractions of the universe may have been effectively sterilized on a regular basis by gamma-ray bursts, the radiation sweeping through young galaxies often enough to repeatedly extinguish any complex life that tried to emerge. By this reasoning, complex life, may simply not have been possible across most of the universe until a few billion years ago, when the burst rate finally dropped low enough and the heavy elements finally built up high enough for life to have both the materials it needed and the calm it needed at the same time. If that is true, then we are not just living in a special place. We are living in a special epoch, one of the first windows in the history of the cosmos, when an advanced civilization could even arise. We may be among the early generations of complex life in the universe, not because life is impossible elsewhere, but because the universe has only recently become safe enough and rich enough to permit it. This line of thinking touches one of the most famous puzzles in all of science, the question of why, in a galaxy of hundreds of billions of stars, many of them older than our Sun, we have so far found no sign of anyone else. If life is a natural consequence of chemistry, the galaxy should be teeming with it, and some of those civilizations should be far older and more advanced than ours, yet we look out and we hear only silence. There are many proposed explanations for this silence, and stellar explosions offer one of the more chilling possibilities. Perhaps the galaxy is not silent because life is rare, but because the universe is periodically wiped clean. Perhaps gamma-ray bursts and nearby supernovae act as a kind of recurring reset button, a cosmic culling that strikes often enough, across long enough spans of time, to repeatedly knock developing life back down before it can rise to the stars. Perhaps the reason we do not see ancient civilizations is that the galaxy does not easily permit anything to grow ancient. This is one of the deepest and darkest ideas in the study of stellar death. The possibility that the violence of dying stars is not just a local hazard, but a galaxy-wide regulator, a force that shapes where and when and whether intelligent life can exist at all. We do not know if it is true, but the fact that it is even plausible tells you how powerful these explosions are, not just as threats to a single world, but as forces that may sculpt the distribution of life across the entire cosmos. And here is the part that should give you pause about our own future. Our safety, real as it is right now, is not permanent, and it is not guaranteed. The Sun does not sit still in the galaxy. It orbits the galactic center, carrying the Earth and all of us along with it on a vast journey that takes roughly 230 million years to complete a single lap. Over that immense circuit, the solar system drifts through different neighborhoods, sometimes through the empty calm of regions like our current local bubble, and sometimes through the dense and dangerous spiral arms where young, massive stars are born and die in great numbers. We happen to be passing through a quiet stretch now, but the geological record, the layers of Iron 60, the patterns of mass extinctions that some researchers have tried to link to our passage through the galaxy, all hint that our journey is not always so peaceful. Over the long timescales of evolution and of civilization building, the Earth will, eventually, find itself once again in a more hazardous part of the galaxy, closer to dying stars, more exposed to their radiation. The threat we have spent this story examining is not a fixed feature of our situation. It rises and falls as we travel, and on a long enough timeline it will rise again. And yet, for all of that, there is a counterweight to the fear, a reason for something other than dread, and it is worth holding on to. Life, once it takes hold, is astonishingly hard to kill completely. We have spoken of stellar explosions stripping away the ozone layer, flooding the surface with ultraviolet radiation, collapsing food chains, triggering extinctions. And all of that is real, and all of it would be a catastrophe beyond anything in human experience. But notice what such an event actually destroys, and what it leaves untouched. A gamma-ray burst or a nearby supernova devastates the surface and the shallow seas, the exposed and the sunlit places where complex, fragile, advanced life tends to live. It does not reach the deep ocean. It does not penetrate kilometers of rock. It does not touch the vast hidden biosphere of microbes that lives beneath the seafloor and deep within the Earth's crust. Organisms utterly indifferent to what is happening in the sky. Organisms that have survived every mass extinction in the planet's history without ever knowing one occurred. Even on the surface, in every past extinction, no matter how severe, something always endured. Life on Earth has been knocked down again and again by asteroids, by volcanic catastrophes, very possibly by the radiation of dying stars, and every single time it has risen back up, rediversified, refilled the empty world and carried on. The story of life on this planet is not a story of fragility. It is a story of relentless, stubborn, almost unkillable persistence. So even the darkest scenario we have considered, a nearby explosion stripping our sky and ravaging our world, would most likely not be the end of life on Earth. It would be the end of a chapter. It would be a culling, brutal and vast, of the complex and the visible, the kind of event that has reset the planet's biology several times before. Life itself, in its deeper and humbler forms, would almost certainly endure, waiting in the dark and the deep for the sky to heal, ready to begin again. The thing that has the most to fear from stellar explosions is not life in general. It is us, and the other large, complex, surface-dwelling creatures who depend on a stable atmosphere and an intact ozone layer. The danger is real, but it is specific, and understanding exactly what is at risk and what is not is part of seeing the situation clearly rather than simply being afraid of the dark. So we arrive at a strange and humbling synthesis. The same stellar explosions that forged our atoms also shaped where in the galaxy we could live, and when in cosmic history we could appear, and perhaps even whether we would have any company among the stars. They are not just a danger to be survived. They are a fundamental force that has structured the entire stage on which the drama of life plays out. We exist in a narrow band of space and a narrow window of time, made possible by stars that died to give us their elements, and protected for now by the simple good fortune of drifting through a quiet patch of the galaxy at the right moment in cosmic history. None of it was promised. All of it could have gone otherwise, and understanding that, truly understanding the razor's edge we balance upon, leads to the final, and perhaps the most important question of all. Not how the universe might end us, and not how it made us, but what we are supposed to do with the brief, improbable, borrowed time we have been given. We have come a long way from where we began, from that countdown clock ticking somewhere in the dark, from the simple and frightening question of whether a dying star might one day end us. And we have found that the answer is far richer and far stranger than the question. Yes, stellar explosions can kill. Yes, the numbers are real, and on the vast timescales of geology and evolution, the universe will, with something close to certainty, eventually aim one of these events in our direction. But we have also found that those very same explosions forged the iron in our blood and the calcium in our bones, scattered the elements that built our world, shaped the regions of the galaxy where life can take hold, and may have helped sculpt the timing of our own arrival in cosmic history. The executioner and the creator are the same. The thing that can destroy us is the thing that made us, and learning to hold both of those truths at once without flinching from either is perhaps the closest thing to wisdom that the study of dying stars can offer. Step back far enough and a remarkable picture comes into focus. For nearly 14 billion years, the universe has been doing this, igniting stars and extinguishing them, building elements and flinging them across space, killing and creating in the same violent breath over and over in galaxy after galaxy, with no one watching. The explosions happened whether or not anything understood them. The elements were forged whether or not anything would ever use them. For the overwhelming majority of cosmic history, this grand and terrible machinery ran in total darkness, unobserved, unmeasured, uncomprehended. And then, on one small, wet, rocky world, circling an ordinary star, the atoms that those explosions had made arranged themselves after billions of years into something unprecedented. They arranged themselves into a being that could look up at the sky, see a point of light, and understand that it was a star. A being that could measure the distance to that star, calculate its mass, predict its death, and recognize, with a jolt of something like vertigo, that the very atoms doing the recognizing had once been forged inside a star exactly like it. After 14 billion years, the universe had grown a way of knowing itself. That is what we are. We are the part of the cosmos that woke up. We are the arrangement of stellar ash that became complex enough to look back at the stars and comprehend its own origin. Every other process we have described in this story is blind. The collapsing core does not know it is collapsing. The gamma ray burst does not aim itself with any intent. The elements do not choose to become life. It all simply happens according to the indifferent laws of physics, without purpose and without awareness. And then there is us, the strangest thing of all, a clump of those same atoms that has somehow become aware, that can feel wonder and fear, that can do mathematics and write poetry, that can sit and contemplate the explosions that gave it birth, and feel a chill run down a spine that is itself made of stardust. We are how the universe asks what it is. We are how the cosmos contemplates its own violence and its own beauty. And as far as we yet know, in all the silent reaches we have managed to search, we may be the only place where that is happening, or one of vanishingly few. This is what raises the stakes so high, and it has nothing to do with the odds of any particular star exploding in any particular century. The danger to us, on any human timescale, is genuinely small. No star close enough to harm us is poised to explode. We are not living under an imminent cosmic sentence. But on the long view, the view that takes in millions and billions of years, the view that the geological record forces upon us, we are a fragile and improbable thing balanced on a razor's edge in a universe that does not particularly care whether we survive. And we are, as far as we know, the only thing of our kind. If we were extinguished, it would not merely be the death of a species. It might be the silencing of one of the few places where the universe had managed to become conscious of itself. The snuffing out of a candle that took 14 billion years to light. The atoms would scatter and persist, as they always do. But the knowing, the wondering, the comprehending, that rarest and most precious thing of all, might simply end. And here is what makes our particular moment in history so extraordinary, and so heavy with responsibility. For every previous generation of humans, the dangers in the sky were utterly beyond reach, not even truly understood. Our ancestors saw the occasional new star blaze into being where none had been, the supernovae of 1054 or 1572, and they wove them into omens and legends because they had no other way to grasp them. They lived their entire lives beneath threats they could neither see nor name nor measure. We are the first. We are the first generation in the entire history of our species, the entire history of life on this planet, to understand what these explosions are, to map where the dangerous stars sit, to calculate the odds, to build neutrino detectors that could give us warning, to even begin to imagine what we might someday do to protect ourselves. We have pulled back the curtain on a hazard that has shaped life across the cosmos since the beginning of time, and for the first time, something that hazard helped create can look directly at it and understand it. That is not a small thing. It may be one of the most significant transitions in the history of life itself, the moment a product of cosmic violence became capable of comprehending and perhaps one distant day of answering it. We cannot today stop a supernova or deflect a gamma ray burst. If a nearby star were aimed at us and ready to explode, there would be little we could do but endure, and even our endurance would be limited. But consider how recently we could do nothing at all, not even know. Consider that the entire science we have explored in this story, the iron 60 in the seabed, the mapping of the local bubble, the tilt of the orbit of the Death Star that turned out to miss us, the neutrino tripwires standing ready in deep mines and beneath polar ice, almost all of it has come into existence within a single human lifetime. We have gone, in the blink of a cosmic eye, from total ignorance to genuine understanding. And understanding is where every form of protection must begin. We do not yet know what our distant descendants might be capable of, with centuries or millennia of further knowledge behind them. But we know they will inherit the understanding we are building now. We are laying the first foundation stones of a kind of cosmic awareness that no living thing on Earth has ever possessed before. We are teaching the universe, through ourselves, to watch the sky. So what are we meant to do with this knowledge, this strange double inheritance of danger and origin? Perhaps the answer is simply this: to look up more often and to look up differently. The next time you stand beneath a clear night sky and see those scattered points of light, remember what you are actually looking at. You are looking at the furnaces that made you. You are looking at objects that are forging, even now, the elements that will one day become other worlds and perhaps other living things. You are looking at a few of them that will, in the fullness of deep time, die in explosions of unimaginable fury, scattering their riches across the dark. And you are looking at all of it with eyes built from the ashes of stars that died long before the sun was born. The light reaching you tonight left some of those stars thousands of years ago, Some of the stars that sent it may no longer exist. You are seeing the past, written in light, by objects that gave you your present. We began with death, with the statistics of annihilation, with the cold and frightening numbers of how the universe might end us. And those numbers are true, and we should not look away from them. But they are only half of the equation, and not the more important half. The fuller truth is that we are here, improbably, briefly, consciously here, because of the very violence we have learned to fear. We are stardust that learned to contemplate the stars. We are the universe, having survived its own creation, looking back at the explosions that made survival possible, and choosing, in the small and precious window of time we have been granted, to understand rather than merely to fear. The same numbers that measure our danger measure our origin. The same explosions that could end the story are the explosions that began it. And in the space between those two truths, fragile and fleeting and aware, is everything that we are, and everything we have ever loved, and everything we might yet become. The clock is still ticking, somewhere out in the dark. It always will be. The question that matters is not whether it will someday stop. The question is what we choose to do, and to see, and to become, in the time we have while it still ticks. Look up, you are made of the same fire, and for one brief moment in the long life of the cosmos, that fire has learned to look back.